1, and we're live.
Awesome. Great. Okay, we're live now. I guess everybody will be able to hear us together with Ben and Heather, Venkat and Hasha. We'd like to welcome everybody to HotNets 2020. We were supposed to host everybody here at the beautiful campus of UChicago. I just want to give us a review and also to the beautiful city of Chicago. It's still a sunshine day here. We very much like to welcome everybody to this awesome workshop and hope to interact with everybody in the upcoming 3 days. Okay, so because this is a virtual conference, this is the first time we experience HotNets, which is highly interactive in virtual conference. We took some liberty to implement some features. We opened up the registration, and with Zoom capacity, we have about 200, and we reached that capacity. Unfortunately, we have to close out that. And for those registered, we will have a live presentation with live Q&As and plus a breakout session where you can continue to interact with everybody on the Zoom in selected groups. And then that's why we want everybody to keep in time so that we can have enough time for the wonderful breakout sessions. And these breakout rooms will happen automatically. You don't need to do anything. It will last about 10 minutes. And that's why we want to keep the time correct. At the same time, we're also doing a YouTube broadcast for general audience. And the breakout session won't be able to do the broadcast because we have multiple rooms, but you should be able to review all the paper presentation and Q&A sessions as well. In addition to the live Q&A, we have a Slack channel, which is open to the general public. As you see from the right side, we have one paper per channel, where you can truly interact with all the authors, the co-authors, and among yourselves. And presenters, please introduce yourself and talk about yourself, introduce your work earlier than your presentation time. And we also have some social events. And before I say that, I wanted to give special thanks to the TPC chairs and the team, steering committee, and our excellent AV staff, and many other behind-the-scenes supporters to make this happen. We would also like to extend our thanks to our sponsors and supporters, ACN, Facebook, Microsoft, VMware. So in addition to the regular technical session, we also have some social events. Microsoft will hosting its own social events, and we have a separate social jobs channel where people can talk about various different like hiring, many other issues, and to interact with each other. Okay, so we'll like to welcome you to Chicago and to HotNets 2020. I will pass my microphone to the two PC chair, which will introduce more about the TPC program. Venkat and Hasha.
Yeah, thanks, Heather. I guess, Harsha, maybe you can project the slides.
Let me share my screen.
Yeah, please do, yeah. So I guess, good morning, good afternoon, and good evening to folks. Thanks for joining. We are really looking forward to this 3-day program. I'm Venkat Padmanabhan with the Microsoft Research India, one of the PC co-chairs, along with Harsha Madhyastha of University of Michigan. And, it's an experiment, like every other conference is doing this year. And, we really want to, preserve the interactiveness of HotNets despite the online format. So we would really encourage you to take advantage of all the excellent work that the general chairs and their team have done in having Slack and Zoom and YouTube, and maximize the opportunity for interaction. So Harsha, why don't you take it over and walk through the program details?
Do you see my screen now?
I see it, yes.
Okay. Yeah, so I guess it won't keep you too long from the exciting program that we have ahead. I'll give you a brief overview of the process that led us to this day. So it started back in June. We had the submission deadline a bit earlier than usual this year. With the hope that we would have an in-person TPC meeting co-located with SIGCOMM. Unfortunately, that proved to be not an option. And back in June, as all of you are well aware, pretty much in most parts of the world, there were stay-at-home orders, and people were affected in various ways. And yet, it was heartening to see we received kind of comparable number of submissions as previous years, like 121 in all. This was spread over more than 150 institutions. So reviewing all of this was of course quite a bit of work, and we are very thankful to the TPC for reviewing all of these submissions in really less than 2 months. Overall, across the TPC members and the external reviewers we recruited, we ended up generating over 500 reviews, which is quite a feat, to be honest, in less than 2 months of reviewing time. And at the end of all this, we ended up with accepting 30 papers. The TPC meeting was virtual, unlike typical years. We ended up having to split it across 2 days as well as a result. And as far as we can tell, this is the most number of papers accepted in HotNets so far. Looking back all the way to HotNets 2002, or if my memory serves me right as to when HotNets got started. So that's all great news. It turns out even for what is a workshop, we had quite a few atypical incidents to deal with, which was a learning experience for Venkat and me and the steering committee and everyone involved. So we thought it's good to share our experiences with everybody. So there's a document that Venkat and I put together. It's shared on the program webpage if you want to take a look. But overall, all of this was really feasible only thanks to a whole bunch of people. Of course, the authors are the ones who I'm most thankful to. Without the ideas they have contributed, we would have no workshop and nothing to discuss here. So thanks to all of them. In addition, really thankful to the TPC members. Again, when the reviewing process was going on, I'm sure all of them had many things to deal with outside of just reviewing HotNets papers, and yet each of them reviewed 25 to 30 papers in less than 2 months. So big shout out to all of them for their efforts. One thing we did do this year, which to kind of complement the TPC's reviewing, was to recruit a fairly large number of external reviewers. Of course, with a small PC, it's kind of hard to ensure we span all areas, and this is particularly challenging in the case of HotNets because authors are typically pushing the boundaries in terms of what is considered in scope for networking research. So beyond the usual suspects like recruiting someone in PL and say machine learning and so on, we also had to end up recruiting external reviewers in areas like robotics, atmospheric sciences. So all of these reviewers responded to our call for help in a very short time frame, like 1 to 2 weeks in most cases. So thanks to all of these for helping us identify and select the best papers to present at this workshop. Last but not the least, really a bunch of thanks to Ben and Heather and their team at UChicago for putting together this multifaceted way of running HotNets. I mean, there's Zoom. We have a live stream to the general public on YouTube. There's Slack. So hopefully in future years, even when we revert back to in-person events, we can leverage all of this functionality. We're also thankful to the steering committee members, Katrina, Sujata, and Dina for all their guidance, and also Ramesh, who was on the steering committee when we got started. And really thankful to all the sponsors and supporters for helping us keep the registration fees really low and making this event possible. That's all I had to say. I hope you find the event useful, and please make sure to interact with all the authors, both during Zoom and on Slack and so on. With that, I guess I'll hand it over to Ellen, who I believe has some remarks to say on behalf of the CARES committee.
Can you hear me?
Yep, go ahead.
Thank you. Thanks, Harsha. Thanks everyone for giving the CARES committee a few minutes on the program this morning. I actually opened HotNets 2016 on the day after the last US federal election. And I have to say that there's a sort of deja vu here that I don't welcome and certainly hope in 4 years from now, if I'm involved in the opening, that that it's not the day after the election. So the SICOM CARES Committee was created about 2 years ago. I think the first event where CARES was represented was SICOM 2018 in Hungary. And this is an effort that got started within ACM SIGs, within the SIG Arch section. And the idea is that a group of folks in the community make themselves available to essentially act as a sounding board or a source of some advice or some consultation for people who may feel that they have been subject to discrimination or harassment, initially targeted towards what might occur at meetings, at our conferences. The scope is, I think, still evolving, and we are still learning the ways that CARES can be most helpful to the community. In general, there are official channels within ACM to make complaints or file grievances. CARES is not. CARES' role is to be available to consult if someone is considering that or thinks that might be a path, or doesn't think that might be a path but would still like to have some support. So and as we've learned over the last 9 months or so, forms of discrimination and harassment are not restricted to in-person settings. They also can happen in virtual settings, and so CARES is relevant in a virtual when we're doing most things virtually, not just when we're in person. These are just a few of the kind of statements supporting racial, social justice. Recognizing that the pandemic is affecting everyone, but some experience it more. And both of these references, of course, to events of the last 6 months. And then the sort of central purpose is to aid in reporting or discussing potential issues of discrimination and harassment. Next slide, please. So there's 6 current members of the committee. I think at HotNets 2020, you'll find Sujata and Justine, although Justine is not here in the opening session, but will be later. I think Marinho may participate. But other members of the committee are also available to you via email. So, if you feel you'd like to reach out to a member of the CARES committee, you can contact any of us, whether we're registered for the particular event or not. So I think that's all I have to say, Harsha, and I wish you all the best for an excellent conference.
Thanks, Ellen. So Heather, I guess we can hand it over to Sergey and get started with the first session. Sounds good.
Thanks, everybody. And we welcome you to the virtual Chicago. Enjoying the workshop.
Okay, well, hello everyone. Thank you, Heather, for hosting the event, and Harsh and Venkat for selecting the program and allowing to be a part of this. So welcome to session 1 on network modeling and experimentation. I'm Sergey Gorinsky from Indian Network Institute in Madrid, and I'm co-chairing this session with Pete Devar from ETH Zurich. So the session will have 5 talks, each 12 minutes long, followed 5 by 5 minutes questions and answers. And after these 5 presentations, we'll have breakout sessions where all of us will be randomly assigned by our hosts, Tom and Caroline from the AV team. So I will briefly introduce each of the speakers. The more detailed bios are available on the Slack channel. The question and answers will be taken through Zoom, so you should be able to raise hand in Zoom. So Pete will be the one monitoring the timing and also issuing auditory warnings. So maybe just to practice briefly. So 2 minutes before the end of the talk, Pete will give the first signal. Pete, can you try? Yes, it's not very loud, but it's audible. Then 30 seconds before the end, Pete, probably can make it a bit louder because at least I can hear very slightly. And finally, if the third signal will sound, it means it's really time to stop, and we'll switch to the questions right after. Okay. So thank you. So essentially, think about your questions. Indicate with raising a hand. We'll also be monitoring Slack channels, but Slack channels of each paper, but we'll give the priority to live questions from the Zoom participants. And with this, let's go to the first presentation. So the first presenter is Thomas Wirtgen. Thomas, maybe you can start switching on your camera and microphone and sharing your slides.
Yes.
Okay, so Thomas is the second-year PhD student with Olivier Bonaventura from UC Leuven. And Thomas is researching protocol extensibility and programmability. And in this talk, he will talk about this topic in the context of BGP. Thomas, please go ahead.
Thank you for the presentation. So I'll speak about BGP, which is a new way to think a network with BGP. So first, BGP is a routing protocol that enables the exchange of routes between 2 autonomous systems. So there are 2 types of BGP session: external one to exchange routes between 2 autonomous systems, and to disseminate the routes between all the routers of the same system. You need to use IBGP, I for internal BGP session. So in one autonomous system, it is very frequent that you have router from different router vendors, and so the BGP protocol must be standardized to support those multiple BGP implementation. But the problem we see later that this standardization will make a big break to the innovation of networks, because those who use this routing protocol are not the ones who implement the protocol. And so, for example, if you would like to add a new functionality to the protocol, such as the geolocalization plugin or features, what you would like to add is when your neighbor announce you BGP update, you would like to add some geographical geolocalization for the routers that receive the update, and you would like to disseminate this information to to your autonomous system to make some, for example, filtering purpose. And then when the route will be announced to your new neighbors, you will send the regular update without the geographical localization. But the problem, if you would like to add this new functionality, you need to first request the feature to your router vendors.
Thomas, your audio is very bad. Could you maybe lower the microphone volume or something?
Is this okay?
It's hard to say, but it sounded better on first sight or on first listen.
It's okay now or not?
Can you move farther from the mic? This is Heather.
Normally it's
Further to the mic. Maybe move further to the mic.
okay.
Not closer, further.
Further. Is it okay now?
No, still the same.
Why don't we continue? I mean, you maybe speak a little less loud and move further from the mic so that your voice will not be distorted. Okay, thank you.
Okay, so I continue. Is it right?
Thomas, that's actually a little bit worse. I think it's the volume of the mic. If you step back a little bit, it might actually lower the volume and make it a little bit better. Right now, there's distortion on the mic.
Is it okay now or?
Yes, that's actually better.
That's better. Okay.
Much better. Thank you.
So I don't need to modify something.
Yeah, please go ahead.
Okay, so when you would like to add a new feature, such as the one I've explained before, you need to pass to the feature request to the router vendors. And so what you need to do is, as being a big network, to ask for the new functionality. But if you are Amazon Level 3 or AT&T, you have a high chance to have your feature accepted. But consider now a small network such as Belnet, which is a small network that interconnects Belgian universities. If you would like to add your feature, then you have a high chance to reject the feature because you don't have enough impacts. And furthermore, if you would like to add a new functionality, you need to go to the standardization step to support multiple BGP implementation. And here on the slide, I picture the standardization delay for some of new functionality of BGP. Then when the standardization part of the protocol, the feature is done, you must wait to the implementation part on the vendor side. And finally, when the update is published, you need to wait to upgrade manually your routers. So furthermore, since you have a lot of routers from different vendors, you have different syntax to configure your routers. So I put here on the slide on the left side, a simple Juniper configuration file, and on the right side, the same for Cisco. However, this is really a pain if you would like if you have a lot of routers on your network, because you need to manually configure each routers. And also, since you have multiple vendor OSs, they do not support the same set of functionalities. So this is really complicated. And what we would like is to move the paradigm and to propose to network operator to inject their configuration file or new functionality directly via a single file that will be dynamically injected to all the routers of the network, independently of the version and the router vendors. And so with this approach, we don't need to restart your routers. And so in a nutshell, what is XBGP is a kind of POSIX now, where your routers is considered now as a microkernel that implements the norm XBGP that accepts multiple plugins and written in a special way. So now we see how to implement XBGP, but what if we would like to add a new functionality, such as the one with the geographical localization? So first, since all BGP implementation is using the same BGP workflow from RFC 4271, we can resonate about that. And in the picture, this is the BGP workflow. So first, BGP message arrive to the routers and go to the data structure called ribbon. Then it will pass to the import filter to apply some policy. And finally, if the route are succeeded to the filter policy, they go to the local rib, where the BGP decision process will take the best route toward each prefix. And finally, you go to the export filter, and when the route is passing the export filter, you need to go to the LG reboot and then generate the BGP message to the neighbors. So if you would like to add your geographication coordinate plugin, you need to add to modify those subparts of the BGP workflow. And what we do is to add some insertion point on each of these standard subflow of the BGP protocol. And actually, your BGP geographical localization is composed on multiple parts. So you have those subparts will be inserted in those insertion points, but that's not all. Because if you would like to add or retrieve some information related to the internal data structure of your router. So, for example, the router geographical coordinates, you need to pass, you need to have a way to make the link between the internal data structure and the plugin. And to do so, we implemented a kind of API, which is called, in our case, libxbgp, that will make this link. And finally, to execute your plugin, we use a virtual machine based on the eBPF bytecode. So now we have seen how to add a new functionality, and we will prove the programmability of XBGP with different use cases. But before, we need to adapt some implementation to make them XBGP compliant. And for this, we use FA routing and BERT. And in this array, you can find all modification or in terms of line of code to make those BGP implementation XBGP compliant. And also when we do this step, we implement some use cases. Here is the list, and I will speak about one of them, which is the value-free path, which is really interesting in the case of data center routing. So data center have kind of different topology as a traditional network, because you have a multi-level topology. And the particularity of those networks is that you use BGP for the intra-routing system. And so one path to go from level 2 to level 0 is the following. You go first to T20, you go up to L11, you go down again, you go up, and you finally reach your destination, which is S1. But the problem you see here that you can have some zigzag path between level 1 and level 2. And the network operator usually don't want to have this kind of zigzag path. And you have internet standard that regroups all of best practices to avoid this kind of path, path. But the problem is that the trick to avoid this zigzag path is to reuse the same autonomous system for each routers for the same level. And so if you would like to make some network debugging, it will be complicated, because if you check the path for the packets, you cannot decide whether if the next hop for this packet is this router or this router, and so on. So this is really complicated if you would like to make some debugging. And so with XBGP, you can actually change this problem, and you can actually use the different autonomous system number to distinguish all the router of the same level of the data center. So what you need to have is first your plugin and one file that contains the topology of all your network. And here you can see on the slide a basic representation of the plugin. It is composed in two parts. The first part is the retrieve data of the host implementation, so retrieve via libxbgp API. And then the core part of the plugin is the while loop, where you check for the zigzag path between inside the data center. And if such a path exists, you tell to the host of implementation to reject the route via a special instruction or a special value. And okay. So to conclude this presentation, we propose a new methodology to upgrade routing protocol. Our methodology is applied for BGP, but could be also used for other routing protocols such as OSPF. We go from a monolithic approach to a modular one, where some part of the routers is exposed to the network operator. And we expect that our methodology will be adopted by network operator. So the next step are the standardization of the API and the virtual machine that we use. And we continue to explore some new use cases to make our methodology as flexible as possible. And you can check the latest update and the source code of XBGP on pluginizedprotocol.org. Thank you for your attention.
Okay. Thank you, Thomas, for the talk. So there should be a button to raise hand. I don't have it on my interface, but you should have it. If you want to ask a question, please raise your hand. So let me, yes, Dave Walker, let me unmute you.
Hi there. I was just curious, the approach seems to depend upon the underlying routers like Juniper or Cisco implementing an equivalently powerful collection of primitives. If you don't have the right primitives in the underlying routers, then you won't be able to implement the new extensions that you would like. Mm-hmm. So I'm just wondering what the current state of affairs is. Are there things you can do on a Cisco router that you just can't implement on a Juniper router, for example? Or what do you have to say about that? Thanks.
Okay, so if I understand the question, you would like to see, to check what is the current limitation of our approach. If it is the case, yes, there is some limitation. For example, if you would like to, for example, modify the internal data structure of BGP, you cannot. Imagine you would like to increase the buffer of reception of BGP messages. This is an example of something that cannot be used now inside our framework. But we keep going to continue to actually propose the flexible implementation of our API to make them possible. And so I think in the future we would like to have something that is really flexible to address this kind of issues.
Okay, so can we unmute Ali? There is a raise hand by Ali Radmand. Ali can speak.
Nice work. I just was wondering, have you measured if these additions cause any kinds of overhead, be it performance overhead or memory overhead? And does it actually matter for this, the BGP execution or not?
Yes, we actually measure the impact of performance. I have some slide about that. So we decided to make some comparison between the native code and some use case that we implemented. So we re-implemented on the blue box the root reflector functionality, and on the orange box the origin validation of roots, kind of RPKI-like functionality. And what we can see is that when you have a lot of sub-plugin, such as the root reflector functionality, actually you have a performance impact of 20%, which is we personally think that is quite reasonable. But the most interesting thing is that for origin validation that is composed on one simple plugin, we have quite good performance for one implementation here in FM routing, but this is just due because the choice of FL routing is to use a native code, a slower data structure to implement the functionality. So our framework can also correct some errors of implementation. So but we expect to have a degradation of performance of 20% in average for the framework.
Thank you.
Okay, so I think we are close to the end of the slot, so it's a good moment to thank Thomas for the presentation. You can continue discussing on Slack, and there'll be also a breakout room at the very end.
Okay.
So thank you, Thomas. So let's go to our second presenter. Ryan, can you try to share your slides?
Yeah, one moment.
Okay, so our second presenter is Ryan Beckett. Ryan is an expert in network verification and synthesis. He received his distinguished PhD degree in the at Princeton University under Dave Walker. Now, for the last 8 years, he is doing the same thing, but as Microsoft research, applying it in Azure. And I guess Brian will tell us something about Zen.
Okay, thank you. Can you see the slides and hear me okay?
Yes, perfect.
Okay, great. Yeah, so thanks for the introduction. I'm going to talk about how we can simplify the process of building, combining and verifying models of network functionality. And this is joint work with Ratul Mahajan. Let's see. So the talk is about modeling, and modeling is the basis of any formal reasoning about networks that we do. And it's the core of network verification tools that can be used to find bugs in networks. And recently, the use of modeling and verification have seen a lot of traction, both in academia, where we now have verification papers routinely visiting our top conferences, and in industry, where we have a rich and vibrant ecosystem now of startup companies, as well as large cloud providers who are leveraging network verification. And it's been used effectively in practice. So for example, at Microsoft, we're routinely verifying changes that we make to our large data center networks. So while verification has found its way into many real systems, what we're arguing in this work is that the way in which we're building our network verifiers today is not ideal. And in particular, the problem that we see is that verification tools today are built as these kinds of massive monoliths where you create your own custom model of some form of network functionality, your own custom algorithms and or translations to solvers and so on to analyze the models. So I'm showing a couple of examples that people may be familiar with from the network verification literature, just to illustrate this design pattern that we're currently using. And this has two very unfortunate consequences. So one consequence of this is that it's very difficult to build new verifiers for new functionality because it requires creating a new model of the component you want to analyze, potentially creating new algorithms or doing a translation to a standard solver, creating new solvers, and so on. And that's unfortunate because networks have a lot of components and a lot of policy that interposes on traffic. So for example, while most of the verification work to date has been focused on layer 3 routing and forwarding, there's a lot more functionality out there. And we believe this is only going to get worse in the future. Now we have, for example, cloud platforms offer a huge variety of ways to add policy to virtual networks, from HTTP filtering and rewriting all the way down to access control. And now we have new technologies like programmable data planes, container orchestration, and so on. And so all of these are increasing the amount of policy and complexity in the network. So that's one problem. The second problem, which is a little more subtle, is that these models that people are building today and the tools are not easily combined. So I can't take a verifier for one component of the network and a verifier for a second component in the network and get out of that a combined verifier for both components in the network. Right, and so this is important because networks are not just one thing in isolation, they're built in layers and you have many components even within the same layer. So in this talk, what we're proposing is the design of a new intermediate verification language and modeling language for network functionality that we're calling Zen. So in our proposed setting, instead, the way we do things is we have multiple network components that are modeled using this modeling language. And then from that, they can be combined in various ways with code. And immediately, a bunch of backends and solvers become available and can be used sort of freely by the user. And combining these becomes simple because everything is done in this uniform modeling language. And this general design is not new. So for example, many people may be familiar with tools like LLVM, which is a very widely used tool chain that compiles multiple source languages into different assembly backends. And even for program verification, researchers have proposed and built various intermediate verification languages, such as Boogie, that have been used successfully in the software domain to simplify verification. So one thing we did, though, is when we looked at some of these existing verification languages that are used in software, and some for networking, what we found is that there are many types of networking verification tools and network analyses that people have constructed that you can't easily model using these existing tools or without modifying the tool's internals. And one of the insights that we had is that there seems to be a little bit of an abstraction mismatch, which is that many of the network verifiers that people have successfully built today, they work in a slightly different way. They work by manipulating large sets of objects, whereas many of these program verifiers work by compilation to constraints that they solve. So we wanted basically an intermediate language that's low level enough that we can represent all of these use cases without any modifications to the internals. So we built a modeling language called Zen, and it's basically a library or an embedded language in the C# programming language. And you just write your functions in C# using this library that the Zen library then automatically knows how to reason about. And so we built a number of backends for Zen, including like a standard model checker, a compiler to assembly, a test input generator, and most notably now we have a new abstraction, which we call state set transformers. So let me give an example of a model in Zen. So models are essentially just functions that you write in C#, but we add this one library type that we call Zen type, that represents a value that can be reasoned about symbolically. So here's an example of a model that we've created for a security group in Azure that's used to filter packets entering or leaving virtual machines. And the function takes 3 parameters. So it takes a security group object in C#. It takes a packet, which is, again, just a class in C# that we've created. But we wrap that packet with the Zen type, meaning we want to be able to reason about that packet. And finally, it takes the line number for the rules that we want to start matching from. And because we can process this function for any packet, the result type is a Boolean saying whether or not the packet is allowed, but it can change depending on the input. So it's also a Zen type. And then the function is fairly straightforward. So we're just saying, if the line number that we're looking at is beyond the last length, beyond the length of the rules, right, then we match nothing. So we return some default action, which in this case would be to deny the packet. Otherwise, we get the current rule, and then we make a call through the Zen library to say, if the packet matches the current rule and it's a permit rule, then we return true. Otherwise, if there's no match, then we continue on to line I+1. So it's a fairly straightforward function that just recursively goes through the rules in the security group. So how do we actually use one of these models? So here what I'm showing is a little bit of code for how to analyze or ask questions about these models. So this is creating a Zen function that asks if a packet is allowed by a particular security group starting at line 0. And this is assuming the rules are in priority order. And then we can do various kinds of reasoning about this model. So for example, here I can say, give me a packet that is allowed by the security group. And I do this through a callback function in C#. So I'm checking if the output of the function is true. And this will either return an example packet to me or tell me that no such packet exists. And that's leveraging various forms of constraint solving in the backend. The other thing I can do is I can reason about sets of objects. So for example, I can ask for the set of all input packets, which will make the output of this function true. And this is very powerful because now I can compute with these sets and I can take their intersection, union, and so on, which is the basis for many of these efficient network verification algorithms. So one other thing to note is that combining these models is very simple. You just need a little bit of glue code that has functions that call other functions. So here I'm showing an example where we're combining a model for forwarding, for access control, and for encapsulation using IPGRE. And we have a more detailed example in the paper. So what's actually happening in the backend is when Zen gets one of these objects, like a concrete network security group, it invokes this function that the user wrote, but it creates placeholder objects for the library types, the Zen types that the user has. And so instead of actually executing the function, it's building at runtime an intermediate representation in the form of an abstract syntax tree. And then it has multiple backends, such as a model checker, a symbolic execution engine, and so on, that I can leverage to run against this AST, encode the result in some pluggable backend, and then translate that all the way back up into C# in a way that is completely transparent to the user. So we had a little preliminary evaluation of Zen. I won't go into too many details here, but we did look at the expressiveness and the efficiency of Zen. And the high-level takeaways were that we can express in basically many of these models of common functionality, like access control, longest prefix matching, route map filtering in the control plane, and so on, in very little code. And in fact, several orders of magnitude less than what many existing verifiers have done. And in terms of efficiency, we found that there's not too much overhead from going through this intermediate representation. So we can actually get fairly comparable results to handcrafted models. In particular, we compared to a model used for ACLs in the Batfish tool. So to conclude, we believe it's going to be very difficult to expand verification to new functionality if we continue with this approach of monolithic modeling. So we're proposing Zen as a way to make this easier, and it's an intermediate verification language for modeling networks. And in particular, we have abstractions that we think will be useful for building high-performance network verifiers. And so we also envision a future where we can basically create many of these models and verify our networks end-to-end by reasoning about their combined behavior. And the tool is completely open source, so you can check it out, and it's packaged, so it's very easy to give it a shot. And with that, I will conclude. Thank you.
Thank you, Ryan. So there is Binje Liu. Can you please unmute him?
Oh, very interesting work. I'm wondering if your language can model control plane protocols like BGP.
Yeah, so that's a good question. So one thing we have done, I think it depends. So one thing we have done is we've modeled, for example, the route map filters in the control plane. So these are the filters that process BGP messages, for example. I think how you would model the control plane could differ. So for example, you could do like a Minesweeper style encoding, which encodes the quiescent state of the network. And you could encode that in Zen. You could also encode sort of like a fixed point in the way that other tools like NV or Shapeshifter, if you've heard of those tools, the way they do that. And the way you would encode that is you would use the state set abstraction to create sets of control plane routes that you would then propagate again until you have a quiescent state in the control plane. So I believe the answer is yes, but I'll caveat that by saying that we haven't actually done that yet.
Yes.
Okay, let's give Ali a chance to ask another question. Ali, go ahead.
Can you hear me?
Yes.
Okay. Hey, Ryan, very interesting work. I was just wondering if all of this modeling is around like packet processing, or can you do more than that? For example, can you model like somehow the traffic, the general network traffic, and somehow reason about that, or it's just about like packet processing and how packets can travel through the network?
Yeah, good question. So there's nothing about this that is specific to packets. So the example with the packet is just packet is just a class I created in C# that then Zen knows how to reason about by analyzing at runtime what fields are in the packet class. So you can reason about things beyond packets, and in fact, we have some work now where we're modeling and verifying some properties of layer 2. So for example, like PFC, if you're familiar with that. So there's nothing, I don't think there's anything here that's, it's intimately tied to packets or anything about, about that, right?
Okay, thank you. More questions? Sorry, let me ask a question. So how is it different from Boogie? You mentioned the racket.
Yeah, so that's a good question. I think in a lot of ways they're very similar. So, Boogie and Racket and like Rosette, if people are familiar with that, they're all fantastic tools. They're very widely used. And in some way we share a lot of the same goals here. I think one thing we found is that, there's certain types of reasoning that seem to be very effective for verifying networks. And they don't seem to be possible in some of these existing tools like Boogie. So that's not to say you couldn't, for example, add this state set abstraction that I was talking about into a tool like Boogie or Rosette. I think you could potentially do that. And I think again, you have a very useful tool. So we kind of came at this from a practical approach, which is, we want to be able to create these verification tools that seem to be very effective and identify that there seems to be a bit of a gap there, right? And so we tried to fill that gap.
Okay, thank you. We have another question from Taran Lin. Please go ahead.
Hi, is there anywhere model physical parts of the layer network within? So like loss or anything like that?
Yeah, that's a good question as well. I don't have a definitive answer. I haven't tried that. I think loss, you might get into a situation where you have to do some sort of probabilistic or, reasoning or something more complicated. So at the moment you couldn't do anything like any kind of probabilistic reasoning or anything that required some more complex reasoning like that. That's not to say you can add, like, for example, right now we have a way to plug in new backends. So maybe there's a way to, add a new backend or new abstractions to the framework to do that. I think it also would depend on exactly how you frame the property you want to check. So for example, if you just need to reason about some finite history of events or of packets, and like whether or not the buffers will get full and so on, that might still be possible. So I don't have a great answer. I think it would just really depend on the specifics.
Okay, thank you, Ryan. And I think we're close to our slot. So unless there is some very urgent question, I would suggest to close this part of the program. Okay, so thank you, Ryan, once again for the nice presentation. And we'll go to the next talk. Yiming, are you there? Can you share your slide?
Sure. Just a sec.
Yes, so our next speaker is Yiming Chiu. Yiming is the first-year PhD student of Ang Cheng at Rice University, Texas. Yiming researchers how to program data planes and predict performance across platforms. So Yiming, please go ahead.
Okay, can you guys see my screen?
Yes, very nice.
Cool. Okay, so good morning, everyone. Today I'll be talking about Clara, which is a tool for performance clarity on SmartNIC offloading applications. This is a joint work between Rice University and the University of Washington. Traditionally, network applications such as Open vSwitch, key value store, and firewall mailboxes reside in host servers. Nowadays, however, we have seen that SmartNICs are gaining fast popularity in data centers and cloud networks. In fact, network developers have been trying to offload the aforementioned applications into SmartNIC platforms in order to save computational resource and energy consumption. Some of the most commonly used SmartNICs include Mellanox Bluefield, Broadcom Stingray, and National Megiddo, along with many others. SmartNICs are very different platforms compared with traditional host servers. First off, in a host server, the computational intensive operations are executed in general purpose and powerful x86 cores, while SmartNICs usually consist of many 1P cores with limited functionality and lower frequency. Additionally, they usually have multiple hardware accelerators to speed up computation. Moreover, host servers usually have enough memory space to save large data structures, while SmartNICs usually have complex but smaller memory space, which frequently leads to partial offloading solutions. On the program model level, host servers support general purpose C or C++, along with packet handlers such as Click, while SmartNICs usually uses P4, other C variants, or even Verilog. SmartNIC platforms are also highly vendor-specific with heterogeneous architectures, program models, and development toolchains. For instance, ASIC-based SmartNIC such as Metronome has micro-engine flow processors, customized NFCC compiler, and P4 plus micro-C program model. While SOC-based NICs usually have ARM or MIPS cores with support for specialized GCC compiler. FPGA-based NICs, on the other hand, usually rely on FPGA card and use hardware description languages such as Verilog. The heterogeneity of SmartNIC platforms have made offloading legacy network function program a daunting task. During offloading, network developers face many hard questions. First off, they would like to know whether NF is offloadable and has potential performance gains. They would also like to know which SmartNIC platform is the best choice, what is the best offloading strategy, and what would be the expected performance after offloading to a particular SmartNIC platform in a certain way. We call this set of important questions performance clarity questions. Today, this set of performance clarity questions could only be answered through exhaustive trial and error. The only way for a developer to understand SmartNIC offloading performance is to go through the whole life cycle of SmartNIC offloading. First off, you need to buy a SmartNIC and obtain access to all its software and documentation. Then, you need to learn its hardware architecture, programming model, and development toolchain in order to understand what the SmartNIC is good at. Now, you can finally start to write SmartNIC programs carefully in order to achieve high performance while preserving the legacy functionality. Last but not the least, you still need to test the performance of the offloaded NF using real-world traffic. If the performance does not meet your expectation, then you actually need to go back to previous steps and look at what is going wrong. This has led us to our research question, which is whether it is possible to bypass this tedious trial and error lifecycle and obtain performance understanding before the development process has started. We are developing a tool called Clara, which aims at providing SmartNIC performance clarity without actually buying the NIC, learning all the databook, or writing any ported programs. Clara takes in legacy NF written for host servers and generate useful offloading hints, as well as corresponding performance profiles. The key technical challenge of Clara is that it's essentially doing complex predictive analysis. The assumption of Clara is that the network developers do not have access to SmartNIC hardwares or their compiler toolchains. Moreover, they haven't written any ported SmartNIC programs. In fact, Clara also assumes that users know very little about SmartNIC optimization and potential tuning efforts. Our observation is that if we do have offloaded NIC program and SmartNIC compiler, then one could easily analyze SmartNIC performance. However, since our tool takes an unported legacy program as the input, Clara needs to closely mimic the behavior of SmartNIC compiler without actual code generation. To that end, Clara takes a four-step approach. It starts with constructing logical NIC for heterogeneous SmartNIC platforms and parsing legacy network function program into Clara IR. Various offloading hints are also provided to the user during this process. Then, Clara mimics the behavior of SmartNIC compiler and try to map Clara IR components into logical NIC model. After the mapping is successful, it plugs in performance numbers such as number of instructions or number of memory accesses obtained by one-time benchmarking efforts to generate performance profile for the control flow. By far, we have finished the introduction to the background and motivation of the Clara project. Let's now move on to our solution sketch. The first design challenge of Clara is the modeling of SmartNIC hardware. To start with, as we have mentioned, different SmartNIC platforms may have completely different architectures. This heterogeneity made it hard to model SmartNIC platforms in a logically uniform manner. Secondly, each SmartNIC consists of many complex components connected with each other through various buses, which made it challenging to model their joint behavior. To resolve this challenge, Clara proposes the concept of logical NIC model. A logical NIC is a graph that represents properties as well as the relationship with SmartNIC components, where each edge could be a compute unit, a memory region, or a switching hub. Each edge could be a memory bus or an on-chip interconnects. In order to reflect the characteristics of SmartNIC platforms, each node and edge contain their own parameters, such as capacity and latency. In practice, we have found this logical NIC modeling could capture most sock-based and ASIC-based SmartNIC platforms. Different physical NICs might have different logical NIC topologies, but the abstraction is almost always the same. The second design challenge Clara faces is how to process legacy NAP programs to make sure they will later be mapped to the logical NIC model. The first obstacle comes from the diversity of NAP program models. Legacy NAPs are written in various libraries and programming languages. Constructing per library processing pipeline is time-consuming and unscalable. The second challenge comes from the distinct components residing in legacy program logic. As shown in this simple example, there could be LPM lookup, header parsing, header field modification, hash function, and checksum in a few lines of code. The task of capturing all of them naturally construct part of our technical challenge. In order to solve this challenge, we have proposed Clara Intermediate Representation, or CIR, whose goal is to model legacy NAP program logics in a program language independent manner. Clara implements several LLVM analysis passes to extract program language independent logic information and tag each components with predefined criteria. Various offloading hints are also provided to the user during this process, reminding them of possible offloading strategies. The third design challenge Clara faces is how to map the CIR into logical NIC components. At a high level, the mapping consists of two parts. Firstly, for stateful data structures, users want to know the number of memory accesses invoked and find their optimal memory space placement in order to achieve high performance on metrics such as latency or throughput. Moreover, for compute operations such as packet header modifications, the user would like to know the performance profile such as number of instructions after compiled by SmartNIC compilers. Clara aims at solving this challenge using a combination of multiple approaches. For stateful data structures and accelerators, Clara will search for optimal placement strategy in the memory hierarchy based on the known resource and speed constraints. We view this as a constraint solving problem and invoke standard ILP solver to search for a solution. For number of memory accesses and number of instructions prediction, we are in the progress of exploring a combination of rule-based methods and machine learning techniques to make an accurate prediction for commonly seen in our programs. The high-level idea is to do an approximate translation from one instruction sequence to another. Now let's take a look at what kind of offloading insights Clara could provide. First off, Clara could provide offloading strategy hints, helping developers build better offloading solutions. Moreover, Clara could also provide performance profile under different traffic workload that's helping users understand the performance of their applications against real-world scenarios. Please note that performance profiling could be very challenging when we consider higher packet rates, interference, scheduling, and auto-order execution. Nevertheless, Clara will still be able to provide useful performance understanding to the users, even if the prediction is imperfect. So by far, we have finished the introduction to the background and solution sketch of the talk. Let's now move on to our preliminary validation. We have done a set of validation on natural GPU CX SmartNICs. As one can see, for the network address translation example, Clara could already achieve hyper accuracy on the task for latency prediction across different packet payload sizes against the baseline manual implementation. Other evaluations show similar early results. Please check out more details in our paper. So to sum up, we are developing a tool called Clara, which aims at performance clarity for SmartNIC before offloading efforts. It takes a four-step approach to mimic SmartNIC compilers by mapping Clara IR into logical NIC model and then plugging in performance profiles. The preliminary validation shows promising early results. With this, I'd like to wrap up the talk. Thanks a lot for your attention, and I'm open to all questions.
Thank you. Thank you, Emin. Anybody wants to ask a question, please raise your hand. Yes. Anup, please go ahead.
Hi, am I audible?
Yes, please go ahead.
Oh, hi. Nice talk. I wanted to ask, like, when you say you build a logical model of the NIC, is that automated, or does the developer of the NIC need to provide these latency values and how many functional units are there for each different types of processing? Or
So the question is, whether the construction of the logical NIC models are automated or not. So a short answer is that it actually involves a lot of manual efforts and expertise for each SmartNIC platforms. But for now, it's actually a one-time effort. So for each SmartNIC platforms, we actually require certain experts to do the logical NIC modeling and to actually insert numbers through benchmarking, etc.
Okay.
Yes, more questions? So let me ask a question. So what if it's not possible to map into SmartNIC hardware?
Excuse me, I didn't really have it.
Yes, so what if it's not possible to map, what if hardware doesn't support some of the functions that the code assumes it's possible to do?
Yeah, so the question is, basically there is a lot of components from the legacy NAV programs that are actually not mappable to SmartNICs due to resource constraint or program language constraints. Basically we are exploring two aspects. The first one is how to do partial offloading, basically how to fit into the resource and problems constraint of the SmartNIC platforms. And the other is really that the primary focus of Clara is more on the core packet handler, which is a core logic ML program. So for now, we don't really model the packet IO such as DBDK, which doesn't really be supported in many SmartNIC platforms. Yeah, so answer is like that.
Thank you. So I see this question from Arjit. Arjit, please go ahead.
So some of the SmartNICs that you're targeting have CPUs, and in general, what we know about CPUs and about the massive effort that has gone into modeling CPUs for compilers is that as we've gone to superscalar out-of-order processing, we seem to do very poorly at modeling them. And, like LLVM and most compilers rely on this, but the accuracy is very low. Why is your logical model able to actually predict anything about performance given this low accuracy when modeling CPUs?
So the question is about the accuracy of the modeling or the prediction Clara makes. So it is true that for many modern CPUs, the prediction or modeling efforts actually have very low accuracy. But the primary goal of Clara is not for a perfect performance prediction. It's more on the performance clarity perspective. For instance, what is the comparison of one SmartNIC platform compared with others, and what is the advantage of a certain offloading strategy compared with others. So we could still be able to answer these questions, even if the performance model is not accurate enough. So yeah, basically that's the answer.
Okay. Just to leave some time for the breakout sessions at the end, let's conclude the Q&As for this talk. So thank you, Yimin. Good luck in your studies. And let's go to the next presenter. Sachin, can you try to share your slides?
Yeah, can you hear me?
Yes, so we can hear you.
Yeah.
And we are into the fourth presentation of the session or the workshop, and only now we'll get to hear about machine learning. So next presenter is Sachin Ashok. He's also a Microsoft researcher. He works with Venkat at Microsoft Research India, and not surprisingly, he's interested in global online services and in particular data-driven network simulations, and that's what he's going to talk about today. Go ahead.
Yeah. I hope you can see my screen and my slides.
Yes, okay. Both are perfect. Slides, sure. And we can see you as well. Thank you.
Got it. So hello, everyone. I'm Sachin Ashok from Microsoft Research India. And today I'll be presenting our project IBOS, which is a short for Internet in a Box, which is about enabling data-informed network simulation. Just to motivate this work a little bit, let me start with the existing state of network simulation. There's a lot of work in the simulation space, and broadly, there are the following distinct approaches. There's work like NS, which really focuses on creating a faithful replication of network components like queues, buffers, and wireless networks, but it is not informed by real data. For example, it doesn't focus on configuring the parameters of these networks realistically. Trace-driven simulation is another possibility where you collect real packet traces and replay them. This is quite obviously informed by actual data, but it is not a realistic recreation of network behavior because the impact of your new application under test is not captured by replay. There's also recent work on calibrated emulators, for example, from Pantheon. We will talk more about this later. So there are limitations with these approaches. So the question is, can we do better? And that's where iBox comes in. So the idea with iBox as a network path simulator is quite simple. We try to build a network model for the end-to-end path between a sender S and a receiver R. For this, we collect per packet traces from real-world applications. We have a packet time series of the sender S, which is just time series of packet send timestamps and packet sizes, and a packet time series of received timestamps of the receiver R. Now, using this data, we train our network models. Once we have network models ready for thousands of such paths, we can then just supply these models to the users. Now, users can try a completely new packet time series, which is, let's say, a new version of their protocol, and get the simulated output from iBox. The key point here is that we do not need access to traces from this new version of the protocol and only need traces from the mainstream protocol to build these network models. So the main goal is to replace the flighting that we do today at Microsoft for applications like Microsoft Teams and Zoom with offline testing, which can mitigate the risk of flighting buggy versions of such networked applications and protocols. And when you grow more confident with your new protocol, you can then flight it to real-world users. Naturally, there are many benefits like speeding up iterations or avoiding regressions and so on. But the main idea is to enable data-informed network simulation. Given this goal, there are a bunch of approaches you can take. The first approach is to use networking domain knowledge to build a very simple networking model and learn its parameters for realistic simulation. The second approach leverages data to build machine learning models to approximate what the underlying real-world network behaves like. There are naturally advantages and disadvantages with both approaches, so we also explore using a combination of networking knowledge and machine learning to get the best of both. There are many aspects of each we cover in detail in the paper, but I'll be focusing only on the few highlighted items in the talk. First, we start simple with iBoxNet. So the idea in iBoxNet is to use a simplified model to capture key characteristics of a network path. So you condense the network path between S and R into a simplified network model, which is then characterized by network parameters like buffer size, bottleneck bandwidth, propagation delay, and also quite importantly, the amount of competition faced on this network, which we will call cross-traffic. Obviously, this is an approximation, but in later slides, we'll see just how well this approximation performs in our evaluation. So let me give you more detail into how some of these parameters are estimated. The basic network parameters I mentioned before are estimated the following way. The bottleneck bandwidth is estimated by tracking the peak receiving rate during the connection. The propagation delay is estimated by analyzing the minimum delay faced by packets in the connection, which likely corresponds to an empty buffer. And the buffer size is then simply estimated based on tracking the productive B, which is the bandwidth, and the difference between the minimum and the maximum delay seen by packets in the connection. Now, naturally, some of these assumptions, like expecting the buffer to be full at some point during the flow, needn't hold in reality. So to mitigate the impact of these assumptions being wrong, we combine information from multiple flows in a given day to get better estimates. Now that we have estimated the basic parameters, we try to estimate the cross-traffic experienced on this path. Roughly at a very high level, the idea is that there are three forces acting on a buffer. The first is our own traffic sending in packets into the buffer highlighted in red. The second is cross-traffic sending in packets into the buffer highlighted in green. And finally, the third is the queue draining packets at the rate of the bottleneck bandwidth. Now, since we know how many packets we sent into the buffer, and we also know the rate at which the queue is draining, we can estimate the cross-traffic experience during this flow. The calculation is done in the following manner, but I will not be delving into details during this talk. So during training, you have all this data that we use to create network models with these parameters. Then we construct a distribution of them, and during simulation, we sample a network configuration from this distribution and construct a network topology. Now, all we need to do is run the new version of our protocol on this topology. So how well does this work? Our evaluation is based off data from the Pantheon TCP testbed operated by Stanford. Pantheon is a distributed testbed with nodes in 9 countries across various networks like cellular, Ethernet, and so on. Stanford runs tests based on many flavors of TCP, like Cubic, Vegas, or BBR, on these real networks every once in a while. And packet traces from these tests are what we use for our training. Our evaluation is in the form of an A/B test. The focus here is on cellular data, which is naturally quite complex and hence very different from the simple iBoxNet model that we've assumed. We use TCP Cubic as our mainstream protocol, which makes sense as it is one of the most widely deployed flavors of TCP on the internet. And we use TCP Vegas as the new unseen protocol, which is a delay-sensitive protocol, and hence is very different from TCP Cubic, which is a packet loss-sensitive protocol. The idea is to use TCP Cubic data to train our models and use TCP Vegas data for our evaluation. So the plots I'm showing here are for the data we collected from Pantheon for the India cellular network. Just to be clear, this is just the ground truth data that I'm showing on this slide. On the left plot, we have rate on the y-axis and 95th percentile delay on the x-axis. And on the right plot, we again have rate on the y-axis and packet loss on the x-axis. Each dot here corresponds to an individual file transfer. The yellow dots are cubic file transfers, and the red dots are Vegas file transfers. The triangles, the squares, and so on that you see in the graph correspond to various percentile statistics. Just to be clear again, this is just the ground truth we are looking at here. And quite clearly, the ground truth shows that TCP Vegas achieves a lower packet delay and packet loss as compared to TCP Cubic, which is as expected from these protocols. And again, to be clear, the yellow dots that we see here are the only traces that we have access to during our training phase. Now, the plots I'm showing here are just the same as before, but with the iBoxNet simulations superimposed on them. So the green dots now are TCP Cubic simulations run on iBox, and the blue dots are TCP Vegas simulations run on iBox. As you can see, there is a good match in the training protocol, but more importantly, we're able to get a good match for Vegas, which is our test protocol, and we're able to successfully predict an unseen protocol's performance. We also ran a case test, and the test did not find a statistical difference between the ground truth and the simulations. So as you can see, even a simple network model is able to predict the performance of an unseen network protocol in a real-world network like a cellular network in India. So earlier, we have talked about cross-traffic being an important component of this simplified network model. Here are some results evaluating the match with and without this cross-traffic component. On the left, we have the same plot from before, but now just with the Vegas calls. The red dots are Vegas calls in the ground truth, and the blue dots are iBoxNet simulations incorporating cross-traffic. And on the right, we have iBoxNet simulations which do not incorporate cross-traffic in purple. As you can see, the percentile values are much worse when the cross-traffic parameter is excluded from the simulation. Earlier, I had talked about work on calibrated emulators, for example, emulators in Pantheon. But a key difference in iBoxNet is that we try to model the root of congestion in the network by modeling the cross traffic explicitly. In addition, we also try to account for behaviors like packet reordering and so on, as you will see in the coming slides. iBoxNet is quite simple and therefore quite fast. It is also interpretable, which is good, but the question is whether it is too simplistic. For example, the cross-traffic model is a static time series, and it is non-reactive to our test traffic. Lack of generalization is another concern. For example, think of packet reordering or burstable bandwidth as examples. Our single queue model is not going to produce any reordering or enforce burstable bandwidth. We can make our network model more and more complex to incorporate it, but then it makes the task of learning the network parameters of this complex network model much more difficult. So that's why we're looking at machine learning to see if we can use it to achieve generalization in the iBox ML approach. So what we're trying to do is to model a network path as a deep state space model using LSTMs. At a very high level, we look at sending rates and previous delay to predict the future delay. We have a multi-layer LSTM that gets sending rates and end-to-end observed delay as inputs. It learns an embedding, which is what we're calling as a state. The state is a representation of the state of our network path. Now, conditioned on this state, there is another network that then samples and outputs the delays for the next time step. This is during training. Now, during prediction, the only difference is that you don't have the ground to delay values that you can feed in. So you have to feed in the output from the previous time step as input for the next time step. This is the general architecture of iBox ML. More details are in the paper. So let me show you an example of the generalization power we talked about earlier using the example of packet reordering. What you're seeing here is the distribution of reordering rates seen in iBoxNet in red, iBoxML in blue, and the ground truth in black. As you can see here, by just trying to fit the delays and without any explicit training to capture packet reordering, machine learning is still able to get a decent match for the distribution of reordering rates, which is the blue line as compared to this red line, which is iBoxNet, which naturally does not produce any reordering as it is a simple FIFO queue. So this shows the power of the machine learning approach. But not everything is perfect with ML either, as there are many challenges as listed here, like the inference speed of the ML model. In the interest of time, I will only be talking about an interesting challenge we have identified called the control loop bias. Control loop bias is an interesting challenge. The idea is that we can collect a lot of real-world data from applications, but these are all tainted by a control protocol. For example, your typical application might have a control protocol which dictates that if it is seeing low delay, it can then proceed to ramp up the sending rate. Now, traces in your training data, which has a sustained high sending rate, will naturally have a sustained low delay. Therefore, what the ML model could end up learning is that high sending rate is what causes a low delay in the network, which is quite clearly incorrect, right? So in order to mitigate this problem, we try to provide our ML models with more networking context, like, for example, the cross-traffic input. This is so that the model knows that there are other factors like the amount of congestion, which determine the delay in the network. As you can see here in the top plot, an ML model which does not incorporate networking context, which is in pink, does not quite match the ground to delay distribution, which is in black. Whereas the bottom plot, the ML model which uses context like cross-traffic input, is able to match the delay distribution much better. This shows that there is a lot of potential for combining networking domain knowledge with machine learning. And therefore, to explore this potential, we now combine network and ML models in order to achieve the best of both worlds. In iBoxNet plus ML, the idea is to use ML to only modulate the operation of iBoxNet. So what we try to do is the following. We have ground truth traces as well as traces from iBoxNet simulations. We pass them both into a behavior discovery module. Now, this module tries to find the diff between these two kinds of traces. Basically, what we're looking for is what kind of behaviors are present in the ground truth but are absent in our simulations. For example, our ground truth might have packet reordering in it, but the simulations may not. So once this module outputs the diff, human experts can then identify the behaviors important to them, like packet reordering, and then we can create purpose-built ML models to incorporate these behaviors into our simulation. So basically, you can set up a cycle of perpetual renewal, where as new data comes in, you can detect new and diverse behaviors, and then keep adding them into our simulations. So let's take packet reordering as an illustrative example. Here we use behavior discovery to identify reordering as an important missing behavior, and then built an ML model which predicts just the occurrence of reordering. We then adjust the iBoxNet delays to achieve the required reordering. This part is the same as before, showing iBoxML getting a moderate match on reordering as a side effect of predicting the delay. Now, using an explicit LSTM model to capture reordering, which rides on top of iBoxNet model, which is the yellow line here, we can see that we're able to get much better performance for iBoxNet. So this shows that we can augment the simple network model with purpose-built ML models to achieve better realism. So to conclude, we feel that data-informed network simulation is an interesting research direction, and the key we feel is to meld networking knowledge with ML to get the best of both. This is an open research area with a lot of scope for future work for us. For example, learning a reactive cross-traffic model, which can react to the new sender under test, or achieving generalization on more interesting behaviors like fair queuing, for example. And finally, also realizing the dream of enabling large-scale A/B tests through iBox. So naturally, there are many interesting research problems, but I hope through this presentation and our paper, we open up a steady inquiry into this area in the community. The iBoxNet network models are available for public download. Please feel free to try these models out. Thank you, everyone. I can take questions now.
Thank you. Thank you, Sachin. So I have a question for Abhijit for a while.
Yeah.
Abhijit, go ahead. Your microphone is on, so you should be able to speak. Hello? Abhijit, are you there? Okay, anybody else? Any other questions from the audience?
Sergey, can I ask a question? Sorry, I can't find my raise hand.
Please go ahead. Please go ahead.
Thanks. Sachin, this is really interesting work. So I had a quick question. I mean, this idea of the feedback loop at the end that you were talking about and trying to sort of look at the diffs and use that feedback to enhance the process. I mean, it seems almost ideally suited for something like a GAN. Maybe not in terms of strict traffic generation, but certainly trying to capture some of the properties in the incoming stream that the initial LSTM has not. Is that something that you guys have looked into or think is possibly promising?
Yeah, so generative adversarial networks are something that we have looked into, but unfortunately, the issue there is that there's no good notion of what you would call as a realistic network trace. So it's hard to build a discriminator which can ideally say what trace is realistic and what trace is not. We can try to create traces where you build simulation traces and feed them in as non-realistic, but then that is implying that those sort of traces can never exist in reality. So it's sort of difficult to come up with a notion of what realistic is, and that's why we haven't really taken a foray into generative adversarial networks. But you're quite right that the modeling idea of behavior discovery is quite similar to how a discriminator would do it.
Okay, thanks.
Yeah. Okay, Fatima, you're next.
Okay, so hey Sachin, a nice talk. And could you please comment on the efficiency of iBoxNet? NS3, for example, is very inefficient at times, but I'd like to know what the efficiency of iBoxNet is. Thank you.
Got it. So typically, the efficiency problems in NS3, NS2 come up because of how big your simulations are and how many events it needs to track per second. But in our case, it would be a very simple like topology where you're setting up just a network path with like a single link, and then you have very few events to track. So it's quite efficient in that aspect.
Okay, so Abhijit, can you speak now?
Yeah, am I audible now?
Yes. Now we can hear you.
Yeah. So I just have one question. How many layers are implemented then? What is the basic layer I can simulate or emulate on this particular simulator? And whether it's actually event-driven or normal, is actually seeing the data. If data is being seen, then how this computation, what is the computation load or computation power required for simulation?
Right. So I will talk about that in two different forms. So first is iBoxNet, which is, so iBoxNet are just configurations that you can use to set up your network topology in NS or NS3 or NetM. And then you can just run your experiment there. So it should be quite fast in NS2 or NS3. Whereas when we talk about iBoxML, that would require, so since it's like a deep LSTM model, that would require a very a reasonably fast GPU. So the issue is that if you're using iBoxML, then for every packet, it needs to make an inference, right? So for example, if your packet is supposed to be delayed for 100 milliseconds, but you take 200 milliseconds to reach that inference, then the packet has already waited for 200 milliseconds. So that's why right now iBoxML cannot scale to gigabit rates, but for low bandwidth scenarios, iBoxML can scale. So iBoxML is clearly more challenging to run as compared to iBoxNet.
Okay. I guess we had already 3 nice questions. So if you have other questions, feel free to ask more questions from Sachin on Slack. So thank you, Sachin. And this brings us to the last presentation of the session. And now I'll present Scott Schenker. Scott, do you think you can try sharing your slides?
Okay, thank you.
Yes. So, yeah, it's kind of a strange thing to introduce Scott. Everybody should know him. And looks like he couldn't make up his mind about many things in life, whether to study physics or computer science, or which topic within computer networking to be started, and even either to work at ICSI or at UC Berkeley. But over the many years, Scott tried to put internet architecture on sound economic ground. So I think this paper has something to do with this as well. So Scott, please go ahead.
Okay, thank you very much. I'll be talking on behalf of my many esteemed co-authors about congestion control, but this won't be your standard, just let me get the, this won't be a standard congestion control talk for 2 reasons. The first is that it's only about congestion control as realized on the public internet. So we won't be discussing schemes that work in data centers. The second is that it isn't about any specific scheme at all, but instead is about how to safely deploy new congestion control algorithms, or CCAs, when they arise. Now, why do I use the word safely? It's because we have a coexistence problem. We have long known that if congestion control algorithms share a congested link, then the more aggressive ones get more bandwidth. And if this is completely unchecked, it can lead to a tragedy of commons kind of situation where congestion control algorithms get increasingly aggressive. So the current approach to combat this is TCP friendliness, or TF, which can be summarized basically as all congestion control algorithms should compete fairly with TCP. Although, see the brilliant paper last year on this topic for a revamping of our understanding. This approach has worked for over 20 years, and I put worked in quotes. It's not perfect, but it's certainly kept us very far away from any kind of tragedy of the commons. But TCP friendliness is in danger from 2 perspectives. Theoretically, we now know, due to Michael Shapira and some of his co-authors, like Radhika, who I think is online now, we know that TCP friendliness restricts what congestion control algorithms can achieve. There's certain kinds of robustness, certain kinds of efficiency you just cannot achieve if you're TCP friendly. So abiding by TCP friendliness limits innovation. And as we get more performance conscious, that's going to be a problem. From a more practical perspective, there are algorithms out there that are widely deployed, such as BBR, that are just not TCP friendly. So TCP friendliness is already being widely violated. Now, the conclusion from this is not that the sky is falling or there's a reason to panic or about to, head into congestion collapse. It's not that at all. It is merely a challenge to us as a community that we should not assume that TCP friendliness will always hold. So we have to address the question that is addressed in this paper, which is, in a world without TCP friendliness, how can we manage coexistence? That is, assuming that TCP friendliness isn't going to last forever, how else do we handle coexistence? Can we prevent increasing aggressiveness? Now, we're not the first to ask this question, and there are 2 main answers in the literature. The first is isolation, or often referred to as per-flow fairness. And this is where each router isolates the flows from each other using fair queuing or its many descendants. And the positives here are the flows can adopt any congestion control algorithm they want because they are neither affected by nor do they harm other flows. The negatives are that the bandwidth allocations you end up with are ad hoc. There's no fundamental grounding for why you end up that way, because why should flows deserve equal bandwidth? They're not the economic entities that we think about. For a longer discussion of it, see Bob Briscoe's blistering and brilliant paper on dismantling a religion, where effectively he calls me an idiot, and deservedly so. The second way of handling coexistence is network utility maximization. This is most closely associated with Frank Kelly, where you charge flows for congestion, and then each flow optimizes its individual utility. The positive here is that you achieve maximal total utility summing over all flows in the internet. The negative is that it is completely orthogonal to the internet's current economics. The internet's current economics is not about flows at all, but involves a recursive series of access agreements. That is, when I send packets from my house, they are carried by my provider because of the access agreement I have. When they leave my provider and they go to the next AS, they are handled precisely because my provider has an agreement with this next provider. So the reason my packet gets from my house to its destination is these series of access agreements. Now, I'm not defending the status quo. If we were to rethink how we might organize the finances or the economics of the internet, we might come up with a different solution. But here we're just accepting it as saying we need to solve coexistence without changing the fundamental economics of the internet. So our approach is to align isolation with internet economics by extending these access agreements. And that is, we assigned congestion shares based on access agreements. And then we use these congestion shares to resolve contention on egress. So these congestion shares are assigned recursively. That is, as your packet travels through the network, it gets assigned different congestion shares as it enters each domain. And I'm only referring to non-terminating domains. I'll come back to that later. So we call this recursive congestion shares, or RCS. So that was a very general description, but if you were to implement RCS, what would a domain do specifically? And there are three very specific things. On egress, a domain assigns a congestion share to the aggregate that's entering, so that from my house, I have an access agreement. All of my packets are considered a single aggregate, and they get a congestion share that's part of the access contract. At egress, isolation using fair queuing-like algorithms are applied to these aggregates based on these shares that you got assigned at ingress. That's the second thing. And the third thing is that these domains try to avoid internal congestion so that the main congestion point is at the egress points. And they already try and avoid this internal kind of congestion. So this applies to all non-terminating domains because we need packets to both enter and leave. And so it doesn't apply to the last hop or the first hop, which might be my house or whatever my packet is going to. Now, to compute these congestion shares, you have to realize that obviously the incoming aggregate, all the packets that are leaving my house, they leave the domain going different places, whether it's Amazon or Netflix or wherever. And so the congestion shares computed at the egress are based on the fraction of my traffic that they represent. Now, we explain this in great detail in the paper with lots of superscripts and subscripts that I won't bore you with, but this is simple example tells you what the basic approach is. If a fraction alpha of my ingress traffic that is leaving my house to my provider exits at a particular egress point, then those packets are treated as having a fraction alpha of my congestion share. It's that simple. That's the mechanism. So we go into many details in the paper. I want to just discuss three of them here. One is that what about these terminating domains? Well, these terminating domains already have an agreement with, the client already belongs to that organization in one way or another. So you can have a variety of approaches. You can mandate a uniform congestion control algorithm. You can deploy isolation mechanisms, which often they already do, or some combination of both. Then why not apply shares downstream, meaning remember that I had more shares than somebody else, several hops downstream. We talk at length about this in the paper, but if I were to rewrite the paper, I would replace that entire section with two sentences, which is, one, the complexity is not worth the benefit, and two, while the allocations may not be theoretically perfect, isolation still holds. And if isolation holds, then coexistence holds. And that's why we don't do it downstream, that it's very complex for not very much payoff. And lastly, how easy is this to deploy? Well, it's only at the edge, not at the core of each domain. So this isn't like the original fair queuing proposals where every router had to do it. It's just the border routers. You can use current router mechanisms that are already used to manage bandwidth. And there's no interdomain agreement or coordination. I, as a domain, I assign shares when packets enter. I enforce shares when they leave. I don't have to talk to anybody else. So what are the benefits? One, we could safely deploy a variety of congestion control algorithms without worrying about how they compete. We don't have to have these long analyses of, in this network of competing against these set of congestion control algorithms, how much bandwidth do they get? Because the bandwidth will be determined by these congestion shares, not by how aggressive your congestion control algorithm is. So it solves the coexistence problem while being completely consistent with today's internet economics. So I want to make two more points in my talk. The first is that we were taken to task by one of our reviewers about ignoring network neutrality. And I want to respond to that in detail, not just to pick an argument. I am argumentative, but that's not why I'm responding. It actually is a very fundamental point that I wish we had addressed in the original version, but we do now. And that is, there are many definitions of network neutrality. The strictest of them is all packets are treated the same. We certainly violate that form of network neutrality. But notice that that form of network neutrality cannot solve the coexistence problem. If you treat all packets equally, there is no way to keep more aggressive congestion control algorithms from getting more bandwidth. So there's no way to solve the coexistence problem without changing the economic arrangements of the internet. However, most network neutrality definitions allow for various forms of traffic management. What they disallow is discriminatory or anti-competitive behavior. This is the EU's BEREC or the Vishal Misra's definition that was picked up by India and other such definitions. We are fully compliant with this definition of network neutrality. Now, the point of network neutrality is actually to one is to keep applications out of the network, but the other one is to be fair. And we explained that, we view these congestion shares as a way to enforce a kind of fairness, whatever you desire. And so you can use equity considerations in how they are assigned. So the last point I want to make is, does anyone care? And here again, our paper, I think, was overly pessimistic. We think the RCS design is desirable and that it solves the coexistence problem and is consistent with economics. We think it's deployable and it can be used by current mechanisms. But will somebody care enough to deploy? Because deploying anything is hard. And so there are two reasons somebody might care. One is domains could offer this as an extension of the service they provide, that we offer you a congestion SLA. And the second, though, is more important, that the people who really care about innovating in congestion control, Netflix and Google and Microsoft and those, they can use their influence to try and convince other domains that if they do this, then we can have better congestion control algorithms and users will be happier. With that, I'm done, and I welcome your questions.
Thank you, Scott. So this paper generated an extensive spirited discussion at the PC meeting, so I expect that there should be some questions from the audience as well. Please raise your hand. We picked close to 100 participants by the end of the session. So Fernando, you should be able, Fernando Ramos. Yeah, you should be able to ask your question now. Fernando, can you speak up?
Can you listen?
You're very, very quiet.
Sorry, can you listen now?
It's a little bit better, but a bit louder would be better.
Okay, so let me try to, sorry.
Speak up as much as you can.
How about now? Is it better?
Much better, yes. Please go ahead.
Okay, excellent. So I had a question about incentives, but I guess Scott already answered with those 2 points, which make a lot of sense. So my main question now is related to what happens if we have internal congestion. So what does it break in this framework?
So it really depends on what kind of internal congestion. If it's long-term persistent congestion, then the bandwidth shares that result may depend on the aggressiveness of your congestion control algorithm, not if you have no kind of isolation internally, it may depend on the aggressiveness of your congestion control algorithm rather than these shares. However, you could put in various forms of isolation, as carriers do now, that can enforce some kind of isolation. So you may not end up with allocations that reflect exactly your congestion shares, but would not be as sensitive to the aggressiveness of your congestion control algorithms.
Thanks.
Okay. So Scott, I have a question. So bandwidth is only one metric of performance. So what if an entity wants to get a low latency? Can it be used somehow? Congestion shares converted to low latency? Because you're tying it to fair queuing, which doesn't really directly give you low latency.
Well, actually, fair queuing does to some extent. That if I'm sending much less than my share, if you really do round robin kind of scheduling, then I get less of a delay than others do. But you're right that if you only enforce the bandwidth, then you don't get the delay. So some of the kind of fair sharing, have a single FIFO queue. But if you actually did round robin, there might be some delay impact.
But also you do aggregation, right? So
yes.
So that's a problem. So you have freight sharing with the other users going through the same aggregate interface.
Yes.
Right?
So we did not take on the sort of the larger problem of sort of service differentiation. We thought this paper was going to cause enough problems without taking that on. I wouldn't know how to do that without running into more problems of fairness easily.
Okay. So I have a question from Giacomo. Giacomo, you're unmuted already. Go ahead. Giacomo? Are you there?
Hello, do you hear me?
Yes.
Okay, great. Thanks for the great talk. So I have a question about policing in general in the scheme. I guess this is mentioned a bit more in detail in the paper, but I just wanted to ask. You mentioned this recursively signed, basically allocations for congestion, and how would they be policed? For example, if I have a certain share alpha, as you said, from my house to the provider, and I forge the share, for example, does the provider have to check every packet and verify signatures recursively for every packet, or how is this envisioned?
Oh, so the shares are typically invisible to the user, meaning that as my packet enters, the domain, either by putting them in an MPLS tunnel or by some border-to-border signaling, says this is the share associated with this class of packets. But I, as a user, never declare my share. So it's all up to the domain, and so they would only be lying to themselves.
And what about lying between domains?
Well, remember that in our scheme, there is no intertalk between domains, meaning a packet comes in, the domain assigns a share, and then on egress, because it controls the egress, it does its sharing. But once it enters the next domain, it is, it's an economic agreement about what share the next domain is assigning the previous share. So that's basically the sort of if a domain says, I'm going to give you a share of, let's say 100 and whatever units that is, but then doesn't, that lying we don't know how to prevent if they just don't give you the share they said they were going to.
Right. Okay, great. Thanks a lot.
Okay, Scott, let me ask the last question before we conclude. So the question about flexibility. So if fair queuing will be put inside of the internet architecture and gets ossified later, could it be a problem? What if you realize later that it shouldn't be there?
So, we wouldn't mandate a particular scheduling algorithm. What we would mandate is that you somehow can enforce the share. So what would be baked into the architecture is that share. Now, one thing I would point out that if domains are doing it just because they're offering some kind of, sort of congestion SLA, an individual domain can offer that or not. But if this became the sort of the accepted wisdom that these sort of shares are the way we allocate bandwidth, to some extent, it is the allocation that would result if everybody sent at their full sending rate. and we just did random dropping at egress. So it's almost the allocations that we were sort of by default allowing. But it's a question we should ask ourselves of how evolvable it could be, and I don't know the answer to that.
Okay. Well, I already said it's the last question, but I cannot say no to Brighton. So Brighton, you have the right to ask the last question of the session.
Sure, Scott, this is a great talk, really appealingly clean idea. So in an ideal implementation of fair queuing, there's pretty clear incentive properties for individual flows. And this is now kind of a distributed implementation of a kind of isolation. So do those incentive properties translate, or are there ways that a flow could game the system?
Well, you mean, are you referring incentive properties like I divide into two flows and do things like that?
Yeah, for example, or any other strategy of, a particular pattern of sending that might depend on what the flow does or the topology or what have you.
I'm not aware of the other kinds of sort of malevolent behavior, sort of manipulations, but there is certainly in standard per flow fair queuing. I take a flow, I divide it up into two, I get twice the bandwidth. That's a bad thing. Here, remember, we're doing it on aggregates at ingress, and that's just if I decide to have two different contracts, that if I give the proportional to the bandwidth, the share is proportional to the bandwidth, then it really is just sort of, what the economic, in other words, my current provider, if I have a 100 meg line and I decide to get two 50 meg lines, just how they do that pricing. But that doesn't strike me as a particularly harmful kind of manipulation, particularly if the incentive is to aggregate rather than to separate.
Okay, so I think it's a good moment to thank Scott for the presentation. There is another question from Sylvester Nadash on Slack, but it's probably the right venue to continue for these and other papers. So before I'll go to the round of thanks, let me tell you what's going to happen next. So I think for those of you who are watching it on YouTube, you'll be not participating. So those who are registered and participating through Zoom, those will be broken up randomly in 5 breakout rooms by our AV host randomly. And we'll have not that much time there, but if you go to breakout rooms, you can switch on your cameras and microphones and have kind of freestyle discussions. So in 10:50 Chicago time, in 13 minutes, the second session will start. So everybody can rejoin there, either registrants through Zoom or the public on the YouTube. And just to conclude, thank you everyone, the presenters for excellently delivered presentations, and especially the audience. It was nice to have these questions in large supplies for the sessions. Please do continue on Slack or reach out directly to the authors and presenters if you have any follow-up questions. Thank you. So this concludes the first session on network modeling experimentations, and thank you for attending.
Okay, hi folks, I'm Radhika Naranjan and I will be co-chairing this session with Noga Rothman. We're both honored to introduce talks and speakers for the session titled Protocols and Architectures. The session has 5 papers and the topics range from the design of data center architectures to enabling use of in-network offloads and revisiting TCP and TLS interactions. So before we jump in, just a quick reminder, please raise your hand on Zoom after the talk if you'd like to ask questions. You can post your questions on the individual Slack channels. They have a prefix November 4, session 2. We will prioritize questions over Zoom, and if time permits, move to the most upvoted questions on Slack. So please upvote those questions on Slack. You will, of course, have an opportunity to engage in the breakout at the end of this session. So with that, let's get to the first paper of this session. It introduces the idea of supporting custom one-sided RDMA calls with SmartNICs. Emmanuel Amaro will be presenting this work. In his words, he is a Mexican 5th-year PhD student at UC Berkeley, where he's advised by Scott Schenker. He's broadly interested in systems and networking, but has mainly focused on remote memory during his PhD. With that, Emmanuel, take it away. I'm asking you to mute.
Sorry, I was muted. Okay. Okay. Hi, everyone. My name is Emmanuel, and in this talk, I will discuss our work in progress remote memory calls, jointly done with my collaborators and advisor. RDMA has recently become more commonly available in data centers and cloud settings. For instance, for some time now, Azure customers have been able to choose RDMA networks for their instances, while Google supports it, at least internally.
Emmanuel, pardon me, but could you share your screen, please?
Oh, it's not shared? My bad. Is now okay?
That's perfect. Thank you.
Okay. Sorry about that. For some time now, Azure customers have been able to choose RDMA networks for their instances, while Google supports it, at least internally. There's 2 main benefits that have caused a wider adoption of RDMA. First, RDMA provides low latency and high throughput to access remote memory, which translates to higher performance on distributed applications such as storage and ML. The second key benefit of RDMA is that its architecture bypasses the kernel and avoids copying data, which leads to reduced CPU usage, particularly on the one-sided RDMA case, as a CPU is not needed on the remote memory side. Applications that use RDMA must choose from a fixed set of verbs or operations that the RDMA stack supports. Send and receive are 2-sided operations, and these require CPUs on both endpoints of the connection. And as I mentioned before, one-sided RDMA only needs a CPU on one side of the connection. Supported verbs by one-sided include read, write, and atomics. And all of these verbs take a remote memory address as argument. So the NIC itself can access the memory in hardware. So consider a distributed application that searches for a key in a remote linked list using RDMA. A one-sided implementation will look as follows. The actors of the diagram will be the client CPU, the server's RDMA NIC, and the server's main memory, which is where the linked list is located. Since we're using one-sided operations, the code to search for the key must reside at the client, as this is the only CPU in the system. The code will read the first linked list node by issuing an RDMA read request. And the RDMA NIC will in turn handle the request in hardware and issue a corresponding PCI read to read the node from memory. Getting the next node in a linked list requires using the next pointer. So every node must be read with an additional RDMA read. If the key doesn't exist, then the code will need to scan the complete linked list, which will result in as many reads as linked list nodes. Okay, for the 2-sided version, first note how the server CPU replaces the server's RDMA NIC in the diagram, so the code can now reside at the server CPU. The client would issue an RDMA send with the linked list key, to search for, and the CPU will receive the request and search for the key. In this case, the CPU can simply issue loads from memory to chase the next pointer. And when the key is found or not found, the server will send a reply back to the client. Therefore, in the worst case with two-sided, there's only one network round trip at the cost of requiring a server CPU, which can be highly undesirable if there's a scarcity of CPUs in your data center. Further, notice how one-sided resembles the shared memory computation model, while two-sided resembles the message passing model. As such, applications, RDMA applications that implement one or the other end up having drastically different designs and implementations. One-sided requires multiple round trips, while two-sided will require a server CPU in the example I showed. So can we do better? We think so. If we had the ability to customize one-sided operations and install them close to the data they access, we could reduce network round trips and perhaps not require a server CPU. So going back to our previous linked list example, what if instead of using vanilla one-sided or two-sided, we could define a new RDMA operation that searches through the linked list for a matching key? But what if in addition to that, you decide you need to count the number of nodes you traverse while searching for the match? And what if on top of that, later on, you decide that you need to sum the traverse nodes keys and return that as well as part of the reply? So instead of providing a fixed set of new RDMA operations, our goal in this work is to allow applications to customize new operations to their applications. In this work, we propose RMCs, which are software memory-oriented procedures. They are registered and invoked by clients at runtime and executed by SmartNIC CPUs. RMCs can access host memory the same way a DMA or RDMA engine can through PCIe. And by providing an API to RMCs so they can read, write, and issue atomic operations, they can access host memory the same way the RDMA engine was able to. In addition, RMCs support program flow control, so conditional branches and loops are possible. And they can keep state in NIC memory, which can be shared across concurrent executions of the same RMC. This could pave the way to support synchronization among SmartNIC CPUs without having to traverse the PCI bus. So let's consider the same remote linked list example from before, but this time with RMCs. In terms of actors, the server's SmartNIC CPU will replace the NIC from one-sided and the CPU from two-sided. Therefore, the code function can be located at the SmartNIC as well. And we call this function the RMC. When the client invokes the RMC, it includes any required argument. So in this case, it includes the key. And in response, the RMC runtime executes the appropriate RMC. Similarly to one-sided, this RMC can read every node from needs to read every node from host memory. But this time, given that the code is closer to data, the PCI can be used directly without its corresponding network traversal. So when the node is found or not found, the SmartNIC can issue a reply determined by the RMC return statement. Okay, so this table here will compare all three implementations I have talked about so far. Similarly to one-sided, RMCs don't use server CPUs and instead use SmartNIC CPUs. In terms of round trips, RMCs match the two-sided case by only requiring the request and the reply to be transferred over the network. In terms of network congestion, this could be a significant benefit over one-sided, of RMCs over one-sided. An enabling trend for our work is the recent proliferation of SmartNICs with faster and more robust capabilities. In particular, we believe future SmartNICs with multi-core CPUs will be the right platform for RMCs. And since we expect the runtime of RMCs to be dominated by memory accesses, SmartNIC CPUs will likely be more performance cost efficient for RMCs compared to server or beefier CPUs. Another feature that RMCs require is a mechanism to efficiently access host memory. And this could be provided by reusing the NIC's RDMA engine or by using a dedicated separate DMA engine that can access host memory from the SmartNIC. Current examples of such platforms are Mellanox Bluefield 1 and Marvell Liquid I/O. So are RMCs really feasible? In particular, can an RMC that issues n memory accesses achieve better performance than n one-sided RDMA requests? To answer this question conclusively, we will need an RMC runtime and measure its performance, which we don't currently have. Instead, here I focus on an analytical argument of hardware capabilities, as this provides the fundamental limitations any system on top will have. So first, in terms of bandwidth, we can expect SmartNICs to have at least as much bandwidth in their PCI bus as they have network bandwidth. For instance, Mellanox Bluefield 1 has two device versions. One that supports 100 gigabit per second over the network, and its PCI bus supports 256. The second device supports 25 gigabit per second over the network, and its PCI bus supports 128. Therefore, we think SmartNICs are very likely to have more PCI bandwidth as they do network bandwidth. And this will give an advantage of RMCs in terms of bandwidth over one-sided RDMA. In terms of latency, note that PCI latency is almost always a component of network latencies. And so we looked at previous studies that reported internal data center latencies and PCI latencies. And we found that a typical latency within a data center is around 25 microseconds. And for PCIe, the worst latency we found is around 1.2 microseconds. Therefore, N PCI memory accesses are likely to be faster than N one-sided requests. So we believe RMCs can achieve better performance than one-sided requests for large number of memory accesses, assuming a low RMC runtime overhead, which I turn to next. A low overhead runtime implementation is critical for RMC's feasibility. And I'll focus on three main aspects. Here. First, memory isolation between RMCs should be cheap. Particularly, thread-based protection will likely be too expensive due to context switch. Previous work in compiler-assisted isolation, such as CVPF, can enable memory protection across RMCs without having to context switch. With these mechanisms, RMCs could be switched in hundreds of nanoseconds. Next, preempting an RMC should be cheap as well. Particularly, interrupt-based preemption will likely be too slow, as this requires thousands of cycles. A better alternative is to have preemption points inside RMCs, for instance, in common helper functions, such as those that provide access to host memory. The last challenge I focus here is the programming language. It should be portable across architectures, similar to C or C++, and statically verifiable. In particular, we're interested in making sure that termination for an RMC is guaranteed within a limited number of cycles, such that RMCs don't loop forever or monopolize a CPU. So far, I have talked about placing RMCs on SmartNICs and the benefits of doing so with respect to one-sided and two-sided RDMA. However, RMCs as an abstraction are small memory-oriented procedures, and they could be located anywhere.
Emmanuel, how long do you have?
This is my, I have this and one last slide.
Okay.
RMCs as an abstraction, are small memory-oriented procedures. So they could be not only located as SmartNIC CPUs, but also as service CPUs, if performance was critical. Another possible location is also at the client CPUs, resembling one-sided. So RMCs are universal in that they can subsume one-sided and two-sided. Current RDMA implementations bake this location decision into their implementations. And once they choose one, there's no easy way to change that without drastic application code changes. With RMCs, applications can be chosen at runtime rather than development time. So they bridge the gap between message passing and shared memory. This ability to switch locations can enable cluster schedulers to react and choose locations based on metrics such as congestion, server CPU availability, and SmartNIC CPU availability. To summarize, here I talked about RMCs, which are memory-oriented procedures. We believe they are likely to be faster on one-sided RDMA for a large number of memory accesses, and they can also be seen as an abstraction that subsume one-sided and two-sided RDMA. Future work, we plan to explore implementing the RMC runtime and the connection to cluster schedulers. Thank you. That's all.
That's great. So waiting for folks to raise hands. And also, if you have questions, please post it on Slack. While we are waiting, I'm going to ask my question because I just have the privilege to. So Emmanuel, at what design points would you recommend that we fall back to RPCs, right, instead of RMCs? are there data sizes or incoming request rates, memory data structures, access patterns that are just better for server CPUs to handle compared to SmartNICs?
Right. So we think RMCs are good as an offload mechanism that makes sense in your context. So as I mentioned in the talk, if you have a scarcity of CPUs, or you don't need the best performance, then we think RMCs could be a very suitable replacement. But also, there's many times when the overhead part of some distributed application can be safely uploaded could be safely uploaded to RMCs without having a big performance impact. As I mentioned in the intro, like storage replication protocols or storage consensus protocol, we think those would be our good candidates to offload. But yeah, if you want best performance and you don't care about using server CPUs, perhaps that's your better choice.
So I think it was related to performance. Are there points where you will not benefit in terms of performance when you use RMC? Are there places where RPCs are clearly more performant and you might just not want to trade off the CPU versus CPU usage versus the performance? I think that's the question that I wanted to ask.
So if you care about lowest latency and if you care about lowest latency and you don't care about the cost of using the server CPU, then two-sided will be it will be very hard to beat because RMCs go through PCIe, right? The main comparison point for RMCs is one-sided, as these usually require multiple network round trips. So we're trying to push the code close to the data so that you can reduce network round trips. And in the paper, we show how it will be possible to achieve better latency compared to one-sided because of these multiple round trips that they require. We still think two-sided has a very valid role. And we think RMCs as an abstraction, since it can capture, so you could write your RMC code once and have it move between being placed at the SmartNIC to be placed at the server CPU, or maybe even placed at the client CPU or the client SmartNIC. So this ability to be moved is one of the main advantages we think of RMCs.
Well, thank you so much.
But the role of, okay.
Yeah, I think you answered my question. Thank you, and we'll continue in Slack. Noga, take it away.
Great, thanks, Emmanuel. This next paper argues for integrating TLS and TCP layers. It will be presented by Florentin Rochet, which is a Belgian computer engineer who recently obtained his PhD in applied cryptography from Lucé Levent Crypto Group. His PhD research focuses on privacy-enhancing technologies such as anonymous communication. Florentin right now is a postdoc at the IP Networking Lab in Lucé Levent, and he's working on extendability, extending the transport protocols. Currently, he's investigating novel options for further progress with TLS and TCP, which is the topic of his talk. So, Florentin, take it away.
Yeah, thank you. I should be unmuted, so can you hear me?
Yeah, we can hear you.
So, yeah, slides should be shared as well. Is it good?
Yeah, we can see you.
Okay, great. So thank you for the introductions, and yeah, welcome everyone to the TCP-less presentation. So this is a joint work with Emria Sogba and Olivier Bonaventures. I will start by giving you a few motivations for this cross-layer TLS TCP. And First of all, the world has changed, and today TCP without TLS over untrusted networks becomes more and more unrealistic. And I think it's mainly due to Let's Encrypt that provides today DV certs to anyone freely and automatically, and to TLS 1.3, which is a major step forward in the TLS series, with, among other things, a formally secure protocol. So those progress may today allow to reconsider merging the stack, which is quite different now than 10 years ago. And so the research question is in this work is what benefit can we gain from merging the stack? And that's not the only motivations. We may also, for example, if we find benefits into improving TCP, we think that it might be great to give TCP a boost to compete with QUIC in the futures, because having two protocols that can compete against each other can be interesting. For example, if you have some improvements in one protocol, which can become useful for the others, which would be a great thing. And regarding TCP, we think that we need to improve the airspace issues for extensibility and the middle box interference problem. And we will see how we can do that. Also, the internet is becoming more and more complex, and application as well. And we think that we lack complex transport features to be exposed to the application. And we want to target that with an API, a new API. Okay, so let's get to more details. So first of all, we want to target a major improvement of TCP extensibility and deployability. And to do that, we define what we call the TCP/LS secure control channel. And essentially, this is a channel that can be used between hosts to exchange options such as TCP options. And this channel has a particularity that it's indistinguishable from application data. And that's a core requirement if we want to avoid middle box interferences. Besides, this approach is at synergy with recent efforts in the Linux kernel for more extensibility in the TCP stack, such that we now have something to propagate options and extensions to TCP between hosts in a secure fashion. We also want an API to export complex transport features, and we want to think about this as composable basic blocks. So to expose features like multi-homing, multipassing, streams, and so on. So we want to take a step back and think about things like the notion of paths, the notion of streams, and what's the application of composing them together, and what the application can gain as properties, right? And finally, we want to show the similarities and the difference between QUIC and TCP/LS. And that's not just about performance, it's also about capabilities. And we will say that actually TCP/LS and QUIC are quite common. So let's dive a bit into the TCP/LS secure control channel and have some example. So the goal was to provide an encrypted and authenticated channel to negotiate TCP extension, but not only TCP extensions. So in this example, we have a simple client and a server. We have an handshake, and the server wants to give knowledge about its IPv6 address. And it just sends these TCP options within the TCP/LS protocol. And it works by using the TLS 1.3 protocol extensibility designs, in which the visible type is still app data. So it's still like an application data message, but the true type is actually located at the end of the payload. So it means that basically you can build whatever protocol structure you want into these payloads. And this will be available inside the handshake, but also at any moment of the TCP/LS session. So regarding the TCP/LS API, our goal was to export complex transport level features to the application. And by export, I mean that the application should be able to make decisions about the transport features it wants. So some applications have different requirements than others, and it should be able to nitpick some features easily. And then, so we have some early results of a few things like zero FTT, multipass, quick live streams, TCP options exchange like new congestion control, PPF bytecode injections, and connection migration. And we are working on all those features. So here's a simple API workflow example between a sender and a receiver. So the first thing to do is to create new sessions, and then you have here an example of a connection. So this is not a zero FTT connection, but a zero FTT is possible as well. So here, the TCP/LS connect function is done in a special composition way, in the way that you can gain something like IPable into this design pretty easily. So when you connect it to the fastest path, you can just uncheck on that path, and you have some callback events that you can register to the transport layer to be notified of what's going on inside the transport layer. And then you can use whatever functions that is available to the applications to interact with the peer, right? So here's one more example about app-level connection migration. So the intuition here is the fact that you can combine what the API offer to perform advanced features. So here in this example, we just need to call 4 API functions to perform migrations to another path. So we have an handshake, a special handshake over a new path to join the connection. And then we just need to create a new stream, attach that streams to the new path, and then close the first path. And then that will effectively migrate the connection. So we did that into a simple network experiment in which we download a 60 megabyte file over this network, and then we switch the paths at the middle of the download. And one of the cool things is this composable features of the design. So in this case, the client just enable multipass mode during the migration. So that means that you don't lose any bytes, and you can migrate much faster into this. And then you're back to only single pass once you are fully migrated. Okay, so now I can talk about a few directions for TCP/LS, a few applicability of these IDs. So one of them is trying, for example, to make a more secure multipass TCP. So if you're not familiar to multipass TCP, it's a protocol that allows to offer a meta socket that gathers multiple TCP connection together. And this protocol has an handshake design that is using clear data. So it just handshake with security parameters sent in clear, which is not great if you want to reach the kind of security that is offered by TLS. And one of the options, if we want backward compatibility, is just simply moving everything you see in red to the control channel of TCP/LS. And then you can have a new set of ops to move data information back to TCP. Or we can also redesign multipass TCP because several of those elements will not be necessary anymore. We could use TCP/LS to detect mailboxes on your path, so, and have a better understanding of the internet. So in this ID, you just have to use TCP option in your header and use the same inside the control channel. And if some spooky middle box change something, then you can just compare and see what's going on. So that's one of applicability. And there is also this pluginizing approach that I think is one of the most promising approach to better extensibility. So this is similarly to Pluginize Quick or XBGP that has been presented a few years ago. And the idea is simply to have some kind of virtual machines that can load dynamic plugins during the connections and change the protocol to the peers or something like that. So you can just send eBPF bytecode and load that code to the peer. So that can be very useful, for example, setting a new symmetric ciphers and so on. And that's really in line with the current the TCP/LS effort to have better extensibility of TCP.
1 minute left.
Yep. I'm coming to my last slide. We also want to think about the efficiency of the cross-layer approach. So intuitively, the performance gain is at the cost of a design complexity. So for example, my implementation can have a zero-copy code pass on the receiver size if the size of the TLS records match the sender window. That means that you don't have any fragmentations on the TLS record, and then you can just give straight away the record to the application. And actually, there is much more possibilities with TCP/LS that I don't have time to talk about it right now. But if you want to stay tuned to the progress, you can look at to those addresses. So with that, I'm done, and thank you.
All right. Thank you so much for being on time, Florentin. So we're waiting for, okay, so we have a question, Fatima Zarini. Let me just, I'm not able to get the, okay, I've asked you to unmute.
Yes, hi. So why do you think TCP/LS is important when we have the QUIC protocol already? Why can't we just use the QUIC protocol or make just incremental changes to QUIC?
Yeah, so thank you for the question. So your question is more about capability. So if we have already protocol A that does something, why do we do a second protocol that will do the same things, right? So one of the motivation, I think, there is it's not just about competition, but that's a good thing to have several protocols in which, if you make any progress in one of them, that will be useful for the others. So that just means that you have much more people working on the same things, and that's a good thing in general. But that's not the only reason. So there will be some difference between those two in terms of performance and in terms of exactly in some situations the properties that you get. So it's not going to be always the same things. And for some reason, for some situation, you may want to use something like TCP/LS that will be much less CPU intensive than QUIC, at least for the next probably the next 20 years. Because the UDP stack still needs to be much more efficient, so that's going to take time. We need the network to have hardware offload for UDP and so on. So that takes time. And in the meantime, I think TCP/LS could be a good thing.
Thank you. We now have a question from Robin Marks. Robin.
Yes, hello.
Yeah, I can hear you.
Thank you for the nice talk, Florentin. I was wondering mainly about one of the innovations you talked about is exposing some of these networking features at the application layer. Yeah. The paper even has like a nice table exposing things like multipath, while very recent discussions with the QUIC working group have been about what is a proper place for this kind of function? Do you really want to expose this to the application? Don't you just want to keep it inside of the transport layer, so to speak, to make things easier for interfacing, that kind of stuff? And I was wondering what your feeling was on that in general.
Yeah. So my feeling is that I think we need to reconsider what kind of feature we want inside the transport layer and what kind of things we want to expose, because it can be useful for having different applications with different needs, only using a set of features and having an API that can let them easily nitpick the things that they need. So of course, there's things that should stay in the transport layer. So for example, reliability, you don't want to expose that to the applications, or even security and stuff like that. But connection migration, that's one thing like I just showed. You can have situation like mobile clients. So just imagine you get out of your car and you arrive at your home, and you basically have two very good networks, the 5G network and your Wi-Fi. And there is no special reason to use one over another. And that at the end, that can be just a user policy, and you can just want to move the connection from one to another from the application viewpoint. That's not something that the transport layer should have knowledge of. It's just something that some application may want to apply. So, of course, we could also enable this kind of setup inside the transport layer, having some kind of interface that just tell, no, I want this connection. And yeah, that's two way of thinking. And I think sometimes it's just easier to expose the features and let the applications do its stuff. Yeah.
Thank you, Robin, and thank you, Florentin. So just in the interest of time, we're going to move on, and you can take more questions on Slack, I think. So the next paper argues for uniform abstractions for implementing application-specific programmable network offloads and describes one plausible solution. Akshay Narayan, a fifth-year graduate student at MIT, advised by Hari Balakrishnan and Mohammad Alizadeh, will present this work. So take it away, Akshay.
Hi, yeah, so thanks for the introduction. And I learned in the breakout room that someone has joined us from Tokyo, where it's 2 a.m. So thank you for staying awake. Okay, so I'd like to start with the observation that in the last several years, we've seen proposals and deployments of a new set of functionality for computer networks, and that is the acceleration and optimization of application-specific functionality. So examples of this are proposals for the hardware acceleration of key value stores, load balancers, and consensus protocols. And these recent developments have been enabled by new devices in our networks, which support a higher degree of data plane programmability. So these are our SmartNICs, P4 switches, and FPGAs. And researchers have shown that placing application functionality on these devices allows them to achieve performance improvements that aren't otherwise possible with traditional end-to-end application implementations. So let's consider the applications that are actually using this new capability. The APIs that our applications use, whether the traditional sockets API or DPDK, or even a higher level library like gRPC or QUIC, they all embody the traditional architectural interface of the internet, which is best effort end-to-end packet delivery. And this mismatch between the interface and the infrastructure means that building and deploying applications that use offloads involves much more than actually just the application. So as you can probably guess, the objective of this talk is to work through this idea. What would an API that encoded the idea of application offloads being inside a network look like? So as we all know, computer scientists have exactly 2 tools to address any problem, and we are no different. So our proposal for addressing this issue is to enhance the application's network interface to perform offload-related coordination. So what we want this interface to do is provide a way to talk about an application's network-oriented functionality. So from the application developer's perspective, they would declare upfront all the network functionality that the application could benefit from. And then from the offload developer's perspective, they're responsible for providing one or more implementations of that functionality. So to see why this interface is necessary, let's see how offload deployment plays out today in an example application. So our server in this application has 2 shard processes, and each shard is responsible for half of the alphabet in terms of requests. So how should we route the client's request to the right server process? And of course, we want to turn to our fancy new network devices. We first have to decide where we're going to implement this sharding based on what's available in the network that our application is going to run on. So for example, there's usually other applications that are sharing the network with us. So we have to consider whether those applications have already staked claims to offload resources that we might have otherwise wanted to use. So now let's say that we decided based on these considerations that we're going to use some particular offload. Now the offload has to actually be written. So in this step, the application developer has to communicate the application's wire format to the offload developer so that the offload can understand our application's packets. Then the system administrator has to configure the hardware to actually run the offload. And then the network operator has to set the routing policy so that the switch or the offload actually processes our application's packets. So the main cost that we can see here is out-of-band coordination. And this is kind of unfortunate because it makes adapting in-network offloads difficult. To deploy such an offload, we need to sit in meetings and send emails until the deployment strategy is actually agreed upon. Then because of all of this overhead and coordination, it becomes harder to change applications. And as a result, they become ossified. So if we started out with a Redis offload, we can't later switch to Memcached because then our offloads would break. So I guess a big thing that we've lost here is portability. If the application assumes the presence of an offload, then deploying that application on a different network requires another round of out-of-band coordination to make sure that the semantics that that application expected from the network are actually still available. And remember that in this example, we've only discussed one part of the application's functionality. So if we wanted to offload another part of our application, we'd have to go through the process all over again. So our answer to resolve this question is a new application network abstraction, which we call channels, and a new interface to that abstraction, which we call Bertha. The idea of a channel comes from the idea of network tunneling, which is widely used today to enhance our vanilla end-to-end delivery with additional network-specific information, such as labeling. So a channel is a fancier version of a tunnel with more rich semantics. Applications use channels by interfacing with Bertha, which is named after the tunnel boring machine in Seattle. Each channel type represents a specific type of application-relevant functionality that can be offloaded into the network. The channel type encodes some semantics which the application wants the network to provide, like the sharding that we just discussed. The key idea behind channels is that on-server and in-network offloads are indistinguishable from the application's perspective, and we should treat them as such. So architecturally, as far as the application is concerned, it really shouldn't matter where the offloaded functionality is implemented, as long as the correct semantics, which are the semantics of the channel that the application specified, are followed. So channels can therefore provide a unified abstraction over all communication-oriented application offloads, no matter where or how they're implemented. So our deployment story from a couple of slides ago, where deploying an offload involved out-of-band coordination, has now become much simpler. So the developer specifies that the application can benefit from a specific piece of functionality in an offload, and the Bertha library makes sure that that functionality is available in the network. So it's important to note that this isn't magic. All of the same work that was happening before is still happening, except now it's in-band and explicit rather than out-of-band and implicit. So when implementing our channel interface, we have 3 goals to keep in mind: portability, safety, and compositionality. We've come up with some rules that channels should follow so that providing these goals is possible. So let's first look at portability. Let's say we have this scenario where our application is running in a network where there are no fancy offloads available. In this case, the functionality still needs to be implemented somewhere, and the only possible place that we have left to us is in software in the application. So we call this property fallback. So while a fallback implementation will probably have worse performance than an offloaded one, it ensures that the application can still function in the absence of a better implementation. So next, the application developer gets to decide which channels that the application wants to use. However, to ensure safety, network operators will still entirely reasonably want to restrict how traffic is forwarded, for example, by using a firewall for security or a billing middle box to make sure that we actually pay for the usage that we're generating. So applications shouldn't be allowed to bypass this functionality as much as we would like to have free access to the internet. And therefore, channels have to be application relevant. And this property is what distinguishes channels from work in NFs or network functions. So while the goal of an NF is to provide functionality that is critical for the network's safe, correct, and efficient operation, a channel's goal is in contrast to aid applications specifically. Finally, compositionality is important because applications often want to use multiple channels together or multiple pieces of semantics together. In this example, the application has specified that it wants a channel with encryption and with HTTP2 semantics and on top of a reliable TCP connection. The application specifies this set of channels so that the semantics of each channel are layered together into a connection, which is Bertha's fundamental unit of abstraction, kind of like a socket. So channel instantiations are per connection. So for each connection that the application is using, Bertha will instantiate an offload configuration that meets the application's requirements for that connection. So how does Bertha work? It has 2 jobs: discovery, which keeps track of the set of channel implementations available in the network, and negotiation, which decides which implementation to use. From the channel implementations perspective, once it registers with the discovery process, Bertha tells it the configuration to use corresponding to a given connection. So I won't go into discovery too much in this talk, but there are more details about how it works in the paper. Instead, let's go a little bit deeper into how negotiation in Bertha works. Bertha gets a set of channels from the application, and it goes through the negotiation process for each of these channels. Negotiation also ensures that for channels requiring it, the functionality that's part of that channel might need to be present on both sides of the connection. So in this case, both encryption and decryption are required on either end of the channel. And there are a number of considerations that we can take into account regarding during negotiation. And this could include a developer preference for hardware offloads, but also the availability of those offloads. So if I try to run my application on a vanilla network without available offloads, then the negotiation would make sure that the fallback software implementation is used instead. As another consideration, the network administrator might want to specify a priority order for the application's use of offloads. For example, we can imagine a cloud provider using the system to offer the use of a P4 switch to higher paying customers as the first priority, but then also allow lower paying customers and their connections to benefit if there's spare capacity. So I'll conclude this talk by going a little bit deeper into some of the open questions that we're excited to find answers to going forward. First, as we saw with negotiation, how should Bertha decide which tunnel implementations to use for a given connection? And this is similar to the role of a cluster scheduler, except now we're scheduling connection offloads instead. There's also the opportunity for optimization, which I'll go into a little bit more deeper next. So let's consider this example where the thanks, Noga. Let's consider this example where the application specified a TCP channel inside an HTTP2 channel, which is inside an encryption channel. And we have a SmartNIC available, which offers implementations for encryption and for TCP. To use these offloads as is, we'd have to traverse the PCIe boundary to the NIC 3 times. First for the encryption channel, then back to the CPU for our HTTP2 implementation, and then back again to the NIC so that we can have TCP semantics. So if Bertha were to rearrange this channel specification, we can then save significantly on our data movement costs. And of course, this idea isn't new to those of you who have seen this kind of thing before. This is exactly the same kind of optimization that's similar to those performed by TensorFlow and ONNX for the machine learning domain and for Weld in the data processing domain. The idea here is that because channel semantics are explicit rather than out of band, we can apply these optimizations to them in a sort of deterministic way. Another cool implementation is that it's entirely semantically valid for the channel implementation to reside not on special hardware, but instead on a cooperating client. So for example, if the server wanted to shard incoming requests, it could push this functionality all the way to the client and remove the need for a fancy offload altogether. And the client would send data directly to the correct shard. In the paper, we show that this configuration can improve scalability and performance. Normally, this would be difficult to adopt because the developer wouldn't want to hard code their sharding policy in a client, which is hard to update. But in this case, because the sharding policy is per connection, offloading to the client doesn't lose us anything. If we wanted to change the sharding policy, we would just update our application, and the sharding policy would propagate through Bertha to the client, which would then use the new policy.
30 seconds.
In summary, yeah, I'm almost done. In the past couple of years have shown that networks can efficiently implement application functionality. And as a result, in this talk, I've argued that it's useful to have an application network interface that exposes network offloads as a first-class consideration. Thank you very much for your attention.
Thank you. That was great talk and great timing, Akshay. So Maria Apostolaki. I'm sorry about the name, the way I pronounce it, but please ask your question.
Hi, Akshay. Thanks a lot for the talk. I really enjoyed it. I was actually wondering whether you also support dynamic requirements for applications. Like, what if I might have a requirement but not always have it, such that you don't have to allocate the resources? Does that make sense?
Yeah, and hi, Maria. I think it depends on how the application is structured. So I think something like a dynamic requirement where, let's say for some connections, I want to use some certain set of offloads, and then for another set of connections, I don't want to use those offloads. I think if the application was written with this in mind, this is something that we could support, because fundamentally, Bertha only cares about per connection what is happening.
Mm-hmm. Okay, thanks a lot.
Okay, while we're waiting for more questions, let me ask mine. So how does Bertha work for in-network offloads in remote switches? Do you eventually foresee that the Bertha runtime will integrate with routing or ECMP network functions?
Yeah, that's a good question, Radhika. So I think like I said in the talk, this isn't magic. So a lot of the coordination that would have to happen still has to happen. So for example, with the question of a remote switch, maybe the mechanism by which Bertha communicates with this remote switch is specified by the offload developer to be like SDN policy or something like that. So it would be basically up to the offload developer to expose their offload, which in this case is a remote switch, in a way that Bertha can use it. Does that answer your question?
Yes, but there's more to it, right? I mean, you would need the runtime to also route all the requests to that particular switch, right?
Yeah, so that's part of what the offload developer is responsible for.
I see. So
when I expose an offload, I don't just expose a device. I expose a device and a way to configure my network so that I can use the device.
I see. Okay, that's great. We still have time, and we are waiting for questions. I'll ask you one more. So where must the discovery service run, and how do you see it being updated as the network is updated? And I think that yeah.
So the discovery service, at least in my head, like maybe if you ask my co-authors, you might get different answers, but at least in my head, the discovery service looks kind of like DNS. So I as an offload, I register myself with this discovery service, and just like I would query for a domain name with DNS, Bertha would query for the availability of some specific offload semantics, which is given some globally unique name.
I see. Well, that's really helpful. I think I'm out of questions. You've answered all of them. So since, we don't have any other questions on Zoom or on Slack, we'll move on to the next speaker. Take it away, Noga. Thanks, Akshay.
Thanks, Akshay. The next paper demonstrates the performance and cost benefits of data plane in network functionality co-design. The work will be presented by Chen Qian. He is an associate professor in the Department of Computer Science and Engineering at the University of California, Santa Cruz. He received his PhD from UT Austin, MPhil from HCOST, bachelor's from Nanjing University, all in computer science. He primarily works on the fundamental problems of computer networks, systems, and security. And he received the NSF Career Awards in 2018. So please take it away.
Thank you very much. So hello, this is my pleasure to present our work, and this is a joint work with my students in my lab at UC Santa Cruz. Okay, so yeah. So in this talk, we are talking about network functions, and which are related to data plan algorithms. And one example of the data plan algorithm is packet forwarding, of course, and most of you are very familiar with it. And also packet measurement, like we want to collect the traffic statistics of the number of flows, or the flow that, the size of the flows, or those heavy hitters in a network. And there could be other network functions like load balancing. So recently we have seen a lot of work in many, the top conferences that are doing research on data plan algorithms, and for example, the packet measurement, and in particular, the sketch algorithms. They are very popular topic in recent CCOM conferences. And also the packet forwarding is also very important once especially when you consider this layer 2 forwarding is different from the IP forwarding, like longest prefix match, they have fixed algorithm. However, if you consider layer 2 forwarding, there could be quite a lot different key value, lookup algorithm that uses a very compact and fast data structures like Bloom filter, cuckoo hashing, and Bloom filter. And this is a recent work from our group called the Ludo hashing in this year's SIG metrics. So all those work focus on this design new data structures and algorithms for individual network functions. For example, packet measurement is just for packet measurement. Packet forwarding is just for packet forwarding. And those are proposed on programmable switches and routers, and also include the software switches that can support network functions. But in fact, we know that a network, router or switch or a that actually serves multiple functions. So, for example, what if you propose a packet measurement algorithm on a programmer switch? Then you need to also assume that the switch does packet forwarding, right? Because every switch does packet forwarding. So our research idea is that what if we put those, we consider the case that those algorithms and data structures, they should be put on the same box, like same programmable switch. Then can we, design some unified or consolidated data plan algorithm and data structures that to serve multiple coexisted network functions? All right. So why this design is possible? Because most of these algorithms, although they serve different objectives, but they have some similar design goals. For example, they all want to achieve space efficiency, right? They want to, because the switch memory is very expensive, because that should be fast to achieve line rate, so it has to be very expensive. So we need the memory space to be compact. And also we want to achieve high throughput to reach line rate. And also these algorithms needs to support dynamic updates because the network is keep changing. And some of them all even share similar computation steps. For example, the algorithm I listed in previous slides, they all needs to compute multiple independent hash functions. Okay, so this is a similarity between different computing steps of those algorithms. And so our idea is that what if we put them together and we use a data structure to serve both forwarding and packet measurement and other network functions, and we can possibly reduce the number of memory access per packet if we store the required information in a same memory unit, like a cache line or same memory unit of SRAM, for example. So that can significantly reduce the number of memory access, and potentially that could be could have some other advantages, and I will talk about it. All right. So one example that we proposed in this paper, although it's a very not quite complete work, but this is our proposal. It's called Lucas, and that's a very simple idea that to put two recent works. One is our Ludo hashing in Sigmetrics, and another is called C-Switch, which is developed by another group from University of Florida on the same session of Sigmetrics that we have heard. So we do a very simple integration of those two algorithms, and we find that the Lucas proposal can actually provide a higher lookup speed and provide a higher accuracy of flow size estimation at the same memory cost compared with running Ludo hashing and C-Sketch at the same time. Okay, so this is a brief algorithm workflow of Ludo hashing that probably will take another 10 minutes to introduce the details, but I will skip the details. If you are interested, you're welcome to go to our papers. But so here we just want to know that it includes several bitmaps and a table, and it requires computing several hash functions, and those hash functions must be independent, and to read several bits or memory units from those bitmaps and the tables. And finally, it can return the value of this key, and this key we identified as F can be considered as a flow identifier, like the for tuple for a TCP packet, or kind of like MAC address, or what kind of a flow, whatever kind of a flow identifier. So yeah, and it requires to compute 4 hash independent, 4 hash functions, and requires 3 memory accesses. And those are very important because this hash function computation and memory access are the bottleneck for the processing speed. And C-sketch is used to estimate the size of a packet. It also includes a table that stores quite a few estimators, and each estimator can even be another bitmap. So, or it can be just a counter, but there are multiple variations. So their workflow is also compute multiple like M independent hash functions and read M memory space, and do the write and read. So these are 2. So what we do is that we put some, the estimators together with the so-called Bloomfield filter, which is a part of the Ludo hashing, and we put some other estimators to the table of the stores the lookup values of Ludo hashing. And eventually we will find that using this design, we can accommodate like M equals to 3. And of course, if you want M larger than 3, you can have 2 more independent, vector for estimators. So that's M can be more than 3, of course. However, even if we only use 3, what do we find is that for a same packet of the identifier, okay, F, and we can access we can put this estimator and these several bits of the Bloomfield filter bitmap together in the same unit. For example, in a software switch, we can put these are put into the same cache line, right? And of course, same cache line can host multiple of the estimators. So that can actually we can use only 3 memory accesses to complete the work of both Ludo hashing and C-sketch. And we show some preliminary results, and we find like this, of course, on software switch. We find that the throughput of this query, number of queries per second of Lucas is significantly higher than the throughput of putting them together, like running them independently. All right.
Okay. Minute and a half left.
Oh yeah. So we have proposed those possible consolidations of the network functions. For example, we can put the FIB with forwarding information base, which is forwarding algorithm, and the sketch together. We can put the load balancer and NAT together. We put load balancer and sketches together. We can put FIB and sketches with samples together. And those are the possible combinations, which we haven't really implemented, but we think that's practical. All right. So, and in future directions, we propose a few like systematical design methodologies that can continually work on this direction. For example, we want to analyze, do network functions apply to the same packet header fields? Do network functions share the same data structure? Do network functions track similar information? And can one feature of the data structure be used by others? So, and also there are some research concerns, issues on the updates and the coordination between the data plan and the control plans. Because all those algorithms requires a coordination. How can we make the coordination more, flexible? And there are more discussions on our paper. And in conclusion, we have we identified that there's a huge space of optimization of consolidated data structures and algorithms of coexisted network functions. And our proposal, Lucas, actually provides 2 times of the throughput and provides higher accuracy based on our analysis, which is also provided in the paper. And we believe more possible consolidations of network function and algorithms can be designed, and we are actually working in this direction. And if you are also interested, we should talk and we can exchange ideas. Thank you.
Thank you, Chen. That was great and beautifully timed. While we wait for questions to appear on Zoom or Slack, so again, I have the privilege to ask you the first question. You've presented a few opportunities for co-design. So do you think a compiler is the right place to identify and implement the consolidations you propose? Or would you also need to know the data plane rules in each network prior to co-design?
Of course, we assume that the rules should be known to the controller, because all those data plane algorithms are basically like programmed by the controllers. So the controller should know everything of those. And we haven't thought about whether different controllers can somehow work interchangeably to do that. But we assume the controller know all the rules of those network functions.
I see. Thank you. Ben has a question.
Yes.
Yes. Hi, Chen.
Hi,
so
Ben.
Nice talk. A quick question. So we see a lot of these co-located sort of functionality mechanisms in cloud and so on, and oftentimes co-locating and sharing mechanisms can be great for performance and sometimes design, but oftentimes leads to some unexpected issues with security and vulnerabilities in particular. So, I was wondering if you guys have thought about that, and what if any are sort of potential isolation mechanisms that you could bring to play to avoid manipulation of one set of mechanisms hashing algorithms results, for example, from leaking into someone else on the same data point.
Yeah, that's a great question. To be honest, we haven't thought about the security problem, but I agree with you. That's definitely is a very valid concern that we should take considerations, like if there is for example, a load balancer and there is another NAT that they are co-located, and of course there could be a security concerns because NAT is very security related. We haven't thought about this problem, but yeah, that could be another research issue we can to work on. Yeah.
Thanks.
Thank you.
All right. People are having trouble raising their hands. Theo Jepson, you're next. Theo, are you on the Zoom call? Okay, there is some. I do see Theo. Can you please unmute? Oh, you can't unmute. Okay, why don't you ask your question on Slack and I will read it out.
Okay, I think I'm unmuted now.
Oh, there you are.
Okay, cool.
So, have you considered how this can be automated somehow? The process of finding commonality and synthesizing a new program.
Yeah, that's right.
And also, you mentioned that you're using that for your evaluation. You used a software switch. Have you thought of other targets, other data plane targets?
Yeah. So the first question, yes, we have identified several methodologies to automatically find if those network functions can be put together. These are several investigations that can be conducted to see if they apply to the same packet header field, or they share similar data structures, they track similar information, or the one feature of data structure can be used by others. All those can be used to identify whether the two network or multiple network functions can be put together. And second question is that, what is that? Sorry, can you repeat? Oh, other than software switches, yes. Well, yeah, we're definitely looking into it. We are trying to first implement it using DPDK, and second, we are trying to use some other programmable switches like Tofino switches to implement our proposed method, but these have not been done yet.
Great. I think that would be the last question we'll take for this talk. Thank you so much, Chen.
Thank you.
Yeah, the final paper of the session shows the performance benefits of getting rid of the spine switches, even for small, or as they call it, moderate scale data centers. Vipul Harsh, a PhD student from UIUC, will present this paper. He is advised by Brighton Godfrey. He is currently interested in network reliability and data center architectures. Previously, he was a spirited undergrad at IIT Bombay. I hope you'll always be spirited, Vipul. Please take it away.
Okay. Thanks for the spirited introduction, Radhika. I'm Vipul Harsh, and I'm going to talk about spineless data centers, which is about topology design for small-scale data centers. So data centers are critical infrastructures, and the data center topology is crucial for the smooth operations of the data center for performance and management related issues. So there are hyperscale data centers, which are commonly built using three-tiered fat tree networks, also known as three-tiered clause topologies. And we also know of alternate topologies such as expanded graphs, which yield higher performance than the three-tiered fat trees, but their adoption has been restricted due to the complexity of management and wiring, and also the requirement of non-traditional protocols for routing and transport. So there are also these small to medium scale data centers, which are actually far more in number than hyperscale data centers. And these are commonly built using two-tier leaf spine architectures, where the top layer consists of spine switches and the bottom layer consists of leaf switches, which are directly attached to servers. Unfortunately, this space of small to medium scale data centers have not been explored explicitly in past works. So in our work, we address the following questions. Are there more efficient topologies than the leaf spine network at small scale? And if yes, can we make them practical in terms of routing design and management complexity? So what are the candidates for efficient topologies at small scale? The most obvious thing is to just try out an expander graph, because we already know that they yield high performance at large scale, and they can be shown to be close to optimal as the size of the network approaches infinity. However, it's not clear if they are necessarily better than leaf spines because of two reasons. One, we are dealing with small scale here, so we don't know if the asymptotic behavior is necessarily true for small scale. And two, a lot of the benefit of expander graphs comes from the fact that they have shorter path lengths than three-tiered clause networks. But leaf spines also have shorter path lengths than three-tiered clause networks. So it remains to be seen if they outperform leaf spine architectures. And we also want to look for other candidates which do not necessarily resemble expander graphs. So before we go into candidates, what are the reasons for expanders' high performance? The first reason is this notion of expansion of a graph, which measures how well connected the graph is. And expander graphs have very high expansion. So high expansion results in shorter paths, which means that the network has to utilize lesser resources to deliver the same traffic, which also helps in keeping traffic well balanced across the network. Expansion also helps in keeping traffic well balanced across the network. That's all. And the second property is the notion of flatness, which means that servers are evenly distributed across all switches. Unlike a leaf spine architecture, where only the leaf switches have servers and the spine switches do not have servers. So in a flat network, there's no spine layer. We just get rid of all the spine switches and hence spineless. So as we'll see in a minute, this even distribution of servers can help in alleviating hotspots during congestion. So how does flatness help? Consider a leaf spine topology as shown. Each rack of this topology has 4 servers and 2 network uplinks. So on average, each server has about 0.5 network uplinks to send its traffic. Let's call this NS ratio, in short for network server ratio. If you do the same exercise for a flat topology built with the same hardware, the NS ratio is 1 because each rack has fewer servers because servers are evenly distributed across all switches, and it has also more network uplinks because fewer servers means that there are some ports which are free. So any flat topology is going to have 2 times more network uplinks per server. And this is true even no matter how you configure the leaf spines. Instead of 2 spines and 6 leaves, you can instead have 3 spines and 5 leaves, and it's going to be the same thing. So what this means is that when the bottleneck is at the Tor uplinks, maybe because of oversubscription, for example, then the flat networks can effectively mask that oversubscription because there is twice as more the exit capacity per rack, per server. So we propose a simple flat network, which for small scale topologies, which we call a D-ring. It consists of supernodes where supernode I is connected to supernodes I+1 and supernode I+2. And each supernode represents a subset of racks. And the connection between 2 supernodes represents the all-to-all connection between the top of the rack switches represented by those racks. And I should note that each switch in this topology is symmetric and all switches are connected to servers. So this choice of D-ring might be a little counterintuitive because its bisection bandwidth is order n worse than an expander, which is contrary to what common sensibilities say, because it's usually believed that higher bisection bandwidth is good for topology design. And we'll come back to this. So how do we route traffic over a flat network? So in a leaf spine topology, there are multiple paths between any pair of racks going through each of the spines. But in a flat topology, there's only one shortest path between 2 neighboring racks, which is the direct link between the top of the rack switches. So if we want to use multiple paths for path diversity, we have to use non-shortest paths. And this problem has also arisen in previous works in the context of expander graphs, since this is true for any flat network. And however, path schemes require extra hardware from or extra functionalities from the network, which hinders practical adoption. So we propose a routing scheme, which we call shortest union K routing, where K is a parameter to the scheme. And the high level idea is simple. Between routers R1 and R2, we use all paths which are either shortest paths or if the length of the path is less than or equal to K. And we show that this can be implemented on essentially off-the-shelf data center switches with very basic data center tools, which are essentially present in all switches. So how can we implement this? Let's say we want to route traffic from R1 to R3, and we want to utilize all available paths. So we are going to use this feature called VRFs. You can think of VRFs as a virtual router instance inside a physical router. And VRFs have been around for about 2 decades. They're present in the standard off-the-shelf data center switches and very commonly used to enforce traffic policies and for segmentation. So we configured 2 VRFs per physical router, VRF1 and VRF2, and we attach the servers to VRF2. And the key idea is that we artificially increase the cost of the direct link between the VRFs which are attached to servers. So the cost of the direct path is 2. And we make all the connections to be 1. So if you want to use the indirect path that goes via R2, you can take all the inexpensive links, and the cost of that path is also going to be 2. So the implementation boils down to configuring these VRFs and then using a shortest path in the VRF graph. And in the paper, we also have a generalization for shortest union K with the same idea. So I'm going to show you comparisons with 3 different topologies, leaf spine, D-ring, and an expander graph, which in our case is a random graph. For the leaf spine, we use a size that's taken from an Arista white paper, and for D-ring and expander, we take the sizes which was the closest possible that we could get to the leaf spine topology. And we want to answer 2 questions through our evaluation. Can flat topologies outperform leaf spine networks? And are there topologies which can be very different than expanders but work well at small scale? So for the first question, can flat topologies outperform leaf spine networks? Here is a plot that shows 99th percentile flow completion time for 5 different traffic matrices, including 2 real-world traffic matrices taken from Facebook. And you can see that if you just use simple shortest path with flat networks, it's not going to work, because there are cases where the performance is very poor. This is essentially the same cases where neighboring racks are trying to talk to each other. So we have to do something better than shortest paths. And you can see here that if we use shortest union 2 routing, it is effectively able to exploit the path diversity in a flat network. And for skewed traffic matrices, when the uplinks of the TOR are bottlenecked, there is a large improvement in the flow completion time with the flat networks.
A minute and a half left.
So I also have some results on throughput, and I'm going to use a traffic pattern called CS traffic pattern, which can be represented on the 2D plane. Each point in the plane C, S is a traffic matrix, where C client hosts are sending to S server hosts. And the reason we use this kind of this class of traffic matrices is that because by varying the values of C and S, we can just get some of the common traffic patterns that have been used in past works. So I'm going to show you a heat map where each point in the heat map represents the throughput of the D-ring divided by throughput of the leaf spine network. And remember that each point in the heat map is a separate traffic matrix. So the thing to look for here are the blue and the dark green regions, which are cases where the D-ring significantly outperforms the leaf spine network. So here is what that space looks like. And if we focus our attention on the first row and column of this heat map, these are cases where many clients are sending to very few servers or vice versa. And essentially that bottlenecks the TOR network uplinks for some racks. And you can see in those cases, D-ring's throughput is almost twice as that of leaf spine, which is also what what our analysis said when we said that the flat network has twice as more the exit capacity per server. We can also zoom in and look at small values of CNS, and we can have the same plots for D-ring with ECMP. You can see, as before, there are regions where D-ring with ECMP does not do well, and these are again the same cases where two racks are trying to talk to each other and they are adjacent. But if you use the shortest union 2 routing scheme, much of that performance gap is gone.
30 seconds.
So coming to the second question, are there classes of topologies besides expanders that work well at small scale? I already showed you that D-ring performs well at small scale. Here is a plot that shows that its performance deteriorates with as we increase scales. And what this shows is that there are classes of topologies which would not work well at large scale, but are still pretty worthy of consideration at small scale. Hence, small scale topology design is fundamentally a different problem than large scale topology design. Okay, so to conclude, there are more efficient topologies than leaf spine, and a lot of benefit comes from using a flat network. More surprisingly, we find out that there are topology classes which are good at small scale, but aren't necessarily good at large scale. So with this opens up a new space of possibilities for small scale topology design that can have better trade-offs for system design. We proposed a practical routing scheme for flat topologies along with a prototype implementation. And I think this is the first such implementation for a flat network. And for future work, we want to see if what's the optimal topology for small scale data centers. We do not claim that D-ring is the best topology. How do flat networks handle failures, and how much can we gain in performance by using adaptive routing or load balancing techniques that have been used similarly for cross networks? So that's it. Thank you.
Thanks, Vipul. So we're waiting for questions on Zoom and Slack, and if people are not able to raise their hand on Zoom, please text us on Slack. So again, I think I will go first. So it looks like you rely on having fewer servers connected to the top of rack compared to the leaf spine topology. So how does your design impact intra-rack workloads that might now have to rely on inter-rack links in your topology.
Yeah, that is true. So if there are cases where you basically have to utilize the network resources, and this is something that we haven't evaluated in the paper, but you would have to the traffic would have to go to the network beyond the top of the rack switch.
Yeah, because I think what I noticed was you use the Facebook workload where they explicitly say that traffic always goes out of the rack. But this is counter to some of the trends where racks are getting, intra-rack traffic can be high for big applications. And it looks like there might be a disadvantage moving to flat networks. Is that your general insight as well?
I think it remains to be evaluated. It depends on traffic, like how overloaded is the network in general. But I think if it's not loaded too much, then it should be fine. The network should be able to handle at least some of the. I don't know what is the exact performance difference, but like if the network is loaded, like every traffic, for example, in the extreme case, if every rack is doing communicating within each other, then that is going to be a problem for sure. But if only few racks are sending traffic, then that might be okay.
Okay.
But you haven't evaluated that explicitly.
I see. Thank you. And I'm still waiting for questions on Zoom, so I'll take unfair advantage. Can you compare the routing configuration changes needed for the leaf spine to this new topology? I see you use multiple VRFs and you set it up. Does that raise the complexity cost of this new network?
So VRFs, VRFs are something that are present in all data center switches essentially. So in terms of like requiring new hardware, it requires the same hardware as ECMP. In terms of complexity, we would have to individually configure these VRFs on every routers, which can be done maybe using scripts, or if there is a software controller, then maybe you can install these configurations. You can basically generate the configurations automatically. So yeah, there is it's a little bit more I would say new compared to shortest paths, and it's definitely a little bit less simpler, but it can be done with basically the same features as what shortest paths require.
I see. Well, Vipul, thank you so much. I think with that, we'll kind of conclude. We come to the end of the session. Thank you, Vipul, for answering all of the questions. We'll now head to the final breakout session. Thanks all for a great first day of HotNets 2020. We'll see you at the breakouts.